how are you doing? Hello and welcome to another stream. How about that? Another session. It's not a stream anymore. I'm not doing streams anymore, okay? I'm doing the coding session, recreational programming sessions. That's what I'm doing right now, today, these days. I don't know. I didn't have enough sleep, okay? So I only had 3 hours of sleep today because of my freaking neighbors. Good lord. Good luck. Good. Yeah, you see, my brain is not working. I don't know how to speak. Gladly, they don't speak English, so they cannot understand us right now. So that's actually pretty fine. So yeah, expect a pretty sleepy stream today. So because I only had like 3 hours of stream. Yeah, today we're gonna do a very interesting topic rather. Today we're going to do a very interesting topic. We're going to continue developing the Wang tile thingy that we started some time ago. So you can find the source code for Wang tile thingy in the chat, and if you're watching on YouTube you can find it in the description. And in the previous episode we actually rewrote Wang tile generator from Pascal to C. Right, so let's take a look at this thing and see if it become better or not. So let's go. So let me see. So Pascal to C. Let me see. Do you publish this session on YouTube? Yes, I do publish them on YouTube. You can find the the link to the channel in here. Origin master, and let's remove this entire thing. So did I actually merge it already? I swear to God I actually merged them. To do for multi-threaded alias generation, Atlas. Yeah, I even created to do, but I don't know. Okay, so that's really weird. I don't know at which point I created it, but apparently I never actually merged it into the real thing. Here it is actually, multi-threaded, so maybe I just don't need this branch anymore. Okay, so let's actually quickly delete it and everything should be fine. So let's rebuild the entire thing, and the idea is pretty straightforward. Right, we have a simple function, right? A simple function that accepts two things. Something that's called BLTR, which is a 4-bit mask that encodes a tile, right? A square tile, where each bit represents the side in the following order: bottom, left, top, right, and 0 and 1 are the colors of the side, right? And the second parameter this function takes, it accepts UV coordinates from 0 to 1, normalized and resolution independent from the tile, and the function is supposed to return the color of this tile description at that particular coordinate within the tile. So you can think of it as sort of like a fragment shader that generates a texture for a particular tile, right? So, and since the tiles have the sides of different colors, these colors determine the constraints of what you can put next to the other tile. It's difficult for me to talk, I really apologize. So essentially you can only place the tiles with the same color on the corresponding sides, right? So that's the colors on the sides form the constraint, and that's basically the idea of the Wang tiles, right? You can read more about this kind of stuff in the repo itself. I left a link to a pretty cool website and stuff like that. So we implemented a thing that generates an atlas of the full Wang tile set. So, and right now it looks like this, right? As you can see, so we have 4x4 atlas, right? Which composes like several 16 tiles. And as you can see, where you have 0, the side is yellow. Where you have 1, the side is blue, right? So, and we have this beautiful atlas, and the next thing we need to do, we need to basically generate a random grid of Wang tiles, right? Satisfying constraints. For example, in the atlas we only store the full set. It does not satisfy any constraints, as you can see. So some of them are not properly like no, not seamless, right? So you can see the seams in here. But now we need to generate a grid that satisfies the constraints, and once the constraints are satisfied, it should look actually seamless and actually pretty cool, right? So it should look like different blobs and whatnot. So hopefully. And once we implement this kind of thing, we're gonna implement some other shaders that generate other kinds of wank tiles, so we can generate pretty interesting patterns. So that's the idea. That's pretty much the goal of this project, is just to play with the idea of wank tiles. And one of the things I wanted to do today, actually, I wanted to parallelize our wank tile renderer, because what we're doing right now, we're actually sequentially going through each and individual tile and single-threadedly, sequentially just generating each tile. But what's interesting is that the tiles in the atlas don't really depend on each other, right? So you can actually generate each and individual tile in a separate thread, right? And since these regions of memory are independent, each and individual thread can just write the tile into their own region of memory without locking anything. We don't even need any mechanisms of a synchronization, right? So you just create 16 threads, and each thread just writes into their own tile, and it should parallelize the whole process. And maybe we can use the same sort of like an engine, like parallel render, to also generate the whole grid as well. Parallelizing with OpenCL, I was thinking to use Posix threads. All right, so the easiest thing to use right now, right? Just basically create 16 Posix threads, and in each thread just generate the tile. So I was thinking about doing something like this. So yeah, so let's first implement the parallel renderer, right? Let's parallelize our renderer, and once we have that, we can move on to generating the actual grid with satisfying constraints and whatnot. Sounds good? Sounds Gucci? Sounds Tamaguchi? Cheers, by the way. So using Posix threads should be fine, since Posix is more portable than you think. It is very portable. Alright, so let me see what we can do in here. So it will start to make sense if you start to have like big tiles. Right now the tiles are not even that big, right? So we can just run the entire thing, and it's actually pretty slow if you look at it, right? If you do time, yeah, it's actually like 2 seconds. But are we optimizing? We don't even optimize anything, right? We didn't even enable any optimizations in here. Maybe one of the things we want to do, first we want to enable some optimizations, maybe some hardcore optimization, as you can see, O3 for instance. Right, so, there we go. Posix threads do not make use of the GPU, right? Probably not. I think they usually make use of CPU. Okay, so did that speed things up? Oh yeah, we're measuring the time of the of the NoBuild as well. So since we enabled more optimizations, now the whole build takes more time, so it's not correct to actually even measure it like that. So if I do something like Wang, it's actually 3 milliseconds, 300 milliseconds, I would say, yeah, 300 milliseconds. Right, but if I disable all of the optimizations, right, all of the optimizations, so what is it going to be? What is it going to be? Let's actually rebuild everything first. Right, there we go. And what do we have? 1.4 seconds versus 0.3. So O3 already optimized some things. Right, so if we're gonna basically parallelize and enable all of the optimizations, I think it could be quite fast. Alright, so yeah, let's enable this stuff back. Let's try to increase the size of the tiles, like 512. So the entire process should go actually slower. It should go a little bit slower, hopefully, because we want to see how it's going. Wang. I forgot to time it. Right. Yeah, it's actually slow. It was like 0.3, now it's 1 second. Right. What about 1000? Alright, so, and if I try to do that... Oh, it is definitely slower, you see? So it becomes slower and slower. What's interesting is that the bigger the tiles, the slower also the part of actually converting this thing into PNG. Because after we generated all of the tiles, right, after we generated all of the tiles, we have to generate a PNG and save everything, right? Otherwise we won't know that we have any sort of result, right? So this is going to be something like black. Output PNG, and there we go. So this is a huge file, actually. What's the resolution of this thing? I think the resolution of this thing is actually quite big. So it's, well, it's 4000 by 4000. 8-bit core RGB. So, yeah, there is a lot of variables that come to play while measuring the time of these things. So, I think it would be better to actually measure the time within the application itself, if you know what I'm talking about, right? So, we don't measure the time of the build, we don't measure the time of the converted to PNG, we only want to measure the time of this specific chunk of code, right? So, and we definitely don't want to measure the time of printing to the std out, because, I mean, it will get affected. Right, so this is a pretty simple region of code, like chunk of code, that just calls to this function, which is also just a simple algorithm, which calls to some sort of a shader, which is also a simple algorithm. There is no even side effects in here, right, except writing into the memory and whatnot. Right, so yeah, we want to time this specific thing, so let's actually go ahead and do that. Manasome, hello. Hello, hello, welcome, welcome, welcome. What should we use to time the execution of this chunk of code, chat? So I heard that people in C use something like clock, right? Yep, clock. Yep, clock. So, and this thing returns basically the clocks, right, which are like microseconds, right? So microseconds since starting the execution or something. Right, so returns the number of clock ticks elapsed since the program was launched. It's a clock ticks, okay. Yep, clock. Yep, clock. So we can try to use that. So essentially you just need to take the difference between, you know, execution of this thing and subtract start from the end and divide it by a clock per second. But usually clock per second is standardized, and according to Posix, if I remember correctly, it is always 1 million. So, well, it would be nice to actually always divide it by clock per second, just to be sure, 100%. All right, so let's go ahead and include the entire thing. Right, so it's going to be time.h and clock t begin. Yep, clock. Then we're going to have a clock end. And oh, it's supposed to be underscore t. It's supposed to be underscore t. Elapsed, and we're gonna actually probably print it in seconds, right? That's why it's gonna be floating point. So we're subtracting begin from the end, and we're converting that to double, and we're gonna be dividing it by clocks per second, right? Clocks per second. Clocks per second. Okay, and that's the elapsed seconds since the you know, since the execution of this entire thing. So generating elapsed generating tiles took LF, right? So L stands for long, F stands for floating point, seconds. Maybe we're gonna say sex, right? LF sex. elapsed, we're gonna provide it in here, and now this entire thing should only time this specific region of code without including PNG, because we can't really optimize anything in here, right? So I basically treat STB as a black box right now. Maybe later we can go into the STB and see what we can do about speeding it up, but to be fair, the point of this project is not really saving PNG, it's basically generating something in the memory, and this is just a way of seeing what got generated in the memory. If we could see what got generated in the memory by looking into the debugger, we probably would use that, but we don't have such good debuggers in 2021, unfortunately, so we have to deal with just saving it to PNG. So it is what it is, and it isn't what it isn't. So let me now try to do NoBuild run, and let's see what's gonna happen. It's gonna take some time, probably. So running Wang. Generated tile took 2.2 seconds. Not bad at all. You know, I would like to also print the size of the tiles, so we know what what exactly the size of the tile we're generating. Bitstream, what's up? So this one is going to be ZU. So tile size is ZU by ZU. Right, and we're going to provide tile width in pixel and tile height in pixels. So now we know what precisely we are generating in here. So it didn't like ZU, so maybe it wants D. Right, so we'll try to rerun it. So it's a compiled tile size 1000 by 1000. Generated tiles took this amount of seconds. Maybe rendering took, and maybe I also want to put a space in here so it's a little bit more readable. Cybercyclonic, hello, how are you? All right, so 2 seconds, and as we get bigger and bigger, right? So we're gonna go to 2048, right? It's gonna get slower. It's gonna get only slower, and we are already using 03, right? So we're already using 03, and it's already really slow. So it's already taking some time. 11 seconds to generate a huge atlas, and also it will take some time to actually save that atlas to a PNG file. I'm not even sure if the image viewer will be able to open such files. So we have a PNG file of the size of 14 megabytes, and if I try to use the file thing on it, it's 8000 bytes. It's not that big actually. I think the modern cameras can produce bigger resolution than that. So I don't know, it's a 8K essentially, so it's a 8K image, so it's not that big, I would say. So if we do something like this, right? Well, Feha is incapable of showing it actually. Oh wait, I think I did a fucky wacky, and quite possibly oopsie doopsie. Okay, so it's actually managed to open it. So this is a pretty huge image, right? And we generated all of these gradients and all of that on CPU and in 11 seconds. Right, so we generated it in 11 seconds, and this is basically what I want to try to optimize, because each individual tile is independent from any other tile. You can literally generate them on separate threads, and we have how many CPUs? I think I have like 4 CPUs here, right? I actually have 2 CPUs, but each CPU has 2 hyperthreads, so to operating system it appears like I have 4 processors, when in reality I have 2. So it's actually a pretty old laptop. I think I bought it in 2013, right? I think that's how old it is. Maybe 2014, right? So I should probably update it. Should have not waited until the shortage of the global shortage of silicon, and should have updated my laptop or my computer a little bit earlier, but it is what it is, and it isn't what it isn't. Okay, so let's try to go ahead and parallelize the entire process. So essentially what we're gonna do, as you can see, we have a loop of 16 iterations in here. So what essentially we're going to do, we're going to take this single iteration and run that single iteration in a separate thread. Straight up. Just a separate thread. Should be pretty straightforward. So maybe we're going to introduce some sort of like, I don't know, macro that defines the mode, right? So for instance, if you defined threaded, we're going to have a threaded mode. So this one is going to be multi-threaded mode, right? Otherwise, this one is going to be single-threaded mode, single-threaded mode. There we go. And then in here, I'm going to just enclose this thing like that. There we go. So, and then we'll be able to switch between single-threaded and multi-threaded and just compare the performances between these two things. Okay, so let's go ahead and do that. As far as I know, you create a new thread in using function pthread_create. Right, it's a very simple function. It accepts the pointer to pthread identifier, some attributes that we don't really care about. You can usually put new in there. I think it configures like how you can cancel the threads and how you can interact with the threads. We don't want to interact with the threads, to be fair. In our case, I want to just throw the input data into the thread and let it do its thing until it finishes, and I don't care. I don't even want to interact with that thread. Right, so I just give it the index of the tile, just generate it in the corresponding area of memory and just die, whatever. I'm not going to even talk to that thread. Right, so which makes this problem actually perfect for parallelization, believe it or not. So, and then we also have to provide the function that performs the actual work, right? So let's copy paste this entire thing. All right. So, but we need to actually have to like have an array of these pthreads identifiers, right? So we're gonna have something like pthread_t, and we're gonna have threads, right? So, and let's say that we're gonna have, how many threads do we want to have? To be fair, we want to have as many threads as there is tiles, right? So I suppose I'm gonna say 16, right? So because the size, the full wank tile set is 16 tiles. Right, and this is going to be 0 initialized. So what we're going to do in here, we're going to iterate through each individual thread. Right. Less than 16 and, all right. Pthreads. So this is going to be threads I. So I'm going to provide the pointer. Attributes, I don't care about the attributes. And we're going to create probably a function called generate tile thread. So this is how we're going to call this specific function. So let's define it somewhere here. So it's supposed to accept a pointer to an argument, and I suppose it needs to return the result. We don't really care about the result of the execution, so I'm going to just return null. And the argument is something that you pass from the thread where you create your thing. So you know what we need to pass? We need to pass this index into a thread. That index is basically BLTR that determines the colors of all of these sides, right? It describes the colors of all of the sides, and it also determines the place in the atlas for the tiles. So a single number gives us a lot of information, and we want to pass that information to the corresponding thread. So usually you pass information via the pointer, just in case you want to pass a huge structure, but we don't really have a huge structure right now. We just have a single number. So you know what we're going to do? I think we're going to do a very stupid thing. We're going to just take that number and reinterpret it as a pointer. Right, so there we go. So I'm taking just number and just reinterpreting it as a pointer and passing it to the thread. So the thread now should know that this is not a pointer somewhere in the memory, but in fact it's an index. It's an index for the tile. So we'll have to do something like BLTR and reinterpret it back into BLTR, and then already work with this BLTR. You know what I'm talking about? So since this thing is such a small thing, we can just pass it as the pointer. We don't need to allocate any memory on the heap, the copy it there, or anything like that. Let's just reinterpret it as a pointer, just pass it in there. It's cheap, it's fast, everyone's happy. See what I'm talking about, chat? Okay. So we created 16 threads, right? We created 16 threads. So after we created them, we need to wait until they're finished, right? We don't want to start saving the atlas until all of the threads have finished. As far as I know, pthreads wait, there was a function pthreads wait. Wait on thread. Okay, I forgot how it's called. Oh, join. Yeah, it's called join. So we need a function pthread join. Oh my god, it's so slow. Emacs is so slow. Okay. All right. So essentially now we have to iterate through each individual thread. ++I. Right, so then I provide the thread in here, so there's gonna be threads I, and I don't really care about the return value because each thread returns null anyway, so who cares? Nobody cares. All right, so that should be the entire thing. All right, so we're just creating 16 threads and we're waiting on those 16 threads, and once they're finished, we take in the atlas, and atlas should contain the final thing. All right. So, and what we're gonna be doing in these threads, we're gonna be doing this entire thing, believe it or not. So we're gonna just copy paste the entire work. BLTR, as already said, determines also place in atlas, right? It determines the place in atlas, and also can be used as the description for the tile. All right, so let's see if we can compile the entire thing. Well, I think I forgot a couple of things in here. So I forgot to time the entire stuff, right? So I forgot to time it. So let's put begin in here, right? Let's put begin, and let's also put this stuff like this. So there is a little bit copy-paste work in here. So maybe what I want to do, I want to extract you know, beginning the measurement and adding the measurement into separate like macros or separate functions. So if I modify something in a way we measure the time, I won't have to do that in two places. So, but for now, it's such a simple thing, I don't really care about that stuff. So, okay, so let me try to recompile the entire thing, and let's go! Ooh. You're really coding on a 2-4 core laptop? Interesting. I don't have much more, at least a decent GPU with features. This is my laptop, if you're interested. You can Google up the model and see what it's doing. I have 8 GB of RAM. So. Okay, so the rendering took 11 seconds in a single threaded mode. I'm also streaming from the same laptop, by the way. So I'm streaming for the same laptop as I code. Okay, so let's actually try to enable the threading, right? Threaded. So now our thing will become threaded. I'm not even sure if it's going to compile first try. It didn't even compile. It doesn't even know what is a pet threads. P threads, not pet threads. Okay, comrade, by the way, in Russian language, the letter P is actually called like P. So yeah, okay, comrade. Did I already mention that I didn't have enough sleep today? So I really apologize if I say something weird, because I'm extremely tired right now. So it is what it is. It isn't what it isn't. So we need to include some of the stuff in here, right? pthread. Let's include this thing. Okay, passing the pointer makes integer from pointer something something. Oh yeah, you don't have to. Okay, you don't have to pass it by a pointer. Oh, this is not enough actually. So you also need to link with the pthread library. Okay, so let's go to NoBuild. Right, NoBuild, and let's add another library, lpthread. There we go. Okay, so let's see if it's gonna do the trick. Multi-threaded mode. 17 seconds. It actually took more than in a single-threaded one. But you know what's weird? I think I know what's going on. I think I know what's going on. It felt faster. Okay, so I'll tell you. I think I know. Please no spoilers. I know some of you probably know what's going on, but please no spoilers. Thread. Right, if I disable it, right. Just look at this thing. It takes some time. It takes 11 seconds, right? Right, it was about like 10. I think we can kill PNG, and then I enable the threaded. Right, I enable the threaded. And okay, so we started the thing, and it's supposed to be 17 seconds, right? But it wasn't 17 seconds. It was way faster. This is not 17 seconds. I think I already encountered something like that before. It's yes. Somebody knows, right? Somebody knows the thing. Somebody knows the drill. So clock doesn't measure really the time, right? So the actual wall clock time, I think this is how it's called. It measures the clocks in CPU. So it also combines the ticks, the CPU ticks from all of the threads. So this is how much time it took for all of the threads combined. That's why it's bigger than a single-threaded one. So, but it felt faster. That's what's important. By the way, we need to check the final result. So does it look okay? Does the final result look? Yeah, final. Oh, that's actually pretty cool. So this is generated using multiple threads, right? This is generated multiple threads, and it didn't corrupt any memory or anything like that. Each thread actually generated the tile simultaneously, hopefully, without any synchronization, because no synchronization I think is needed in this particular case, right? Because they just like don't overlap with each other, right? So everyone is just generating things into their own slot of the memory. So let me see. So we need to actually measure time slightly differently, right? So clock. So do you have? I think you can use get time. Yeah, I remember this thing. You can use get time, and you can even provide different sort of clock IDs. So you can have like a real time. Yeah, we can probably use a real time. Or maybe there's also monotonic. Yeah, a clock that cannot be set and represents monotonic time since someone's unspecified starting point. Okay. So that's the thing we can use. The problem with this thing is that it's Posix, right? It's not a part of the C standard, right? But it's a Posix. But as we know, Posix is more portable than you think. So maybe we can depend on that. So it's a throwaway code anyway, right? It's a throwaway code anyway. We're just trying to explore how would you render wank tiles and also learning about multi-threading and whatnot. So I guess it's okay to depend on these kind of things, right? And if you want to compile this on Windows, just use WSL. I guess Windows is turning into a Linux distribution anyway. So yeah, it is what it is, and it isn't what it isn't. Is it not? I think it is. So, you know what? So now measuring the time, look at this function. This function is more complicated than just clock. Right, so clock would just return you some shit and you would just save that shit, but now you have to, look, you have to provide the clock ID, monotonic, right, so this is going to be the monotonic shit. There we go. And then now we have to provide the pointer to a structure. So our structure is going to be something like begin, right? So we provide the pointer. There we go. So this entire thing can also return an error. So -1 in case of an error. So if less than 0, right, you have to crash, saying something like could not get current time because of this thing, and we can do str error error no, and then crash. Right, so it becomes really complicated. So which makes me think maybe we want to extract all of that to like a separate functions, like begin measure time and like end measure time, and the when you invoke end measure time it will just show the elapsed time. If you know what I'm talking about, On Mac OS is not portable. Stop using closed source operating system. So why it's always with Mac OS and Windows? Just use a normal operating system like normal human being. Come on. Everything is portable on Linux. Alright, so I think we need to extract some shit, right? We need to extract some shit. So I just want to have a simple global function, like begin measure time, right? Begin measure time. And then end measure time. There we go. So you know what? I think I'm gonna create like a global variables. I don't really want to pass any parameters in here. I think it's a waste of time, right? So this is just like a debug code anyway. So yeah, let's just create two global variables, something like clock begin and clock end. And maybe I'm gonna actually call this entire thing begin. Fuck, it's actually I wanted to call it begin clock and end clock, but now the name is actually like this thing. Let's actually call it TS. Is it TP? I remember that the get time, right? Get time called it. It calls TP for some reason. Okay, so we're gonna call it TP begin and TP end, and this is begin clock and end clock. All right, so the way it's going to work, we're gonna say get time, right? So we're getting the time, and the time is monotonic, right? So this is a monotonic time, and we provide the pointer to the begin, TP begin. So, and if it fails, we're gonna crash the whole thing, right? Just to know what the hell has happened. Since these functions are not executed like very often, this checks is fine, right? It's not gonna slow down anything, I think. So std error error could not get current monotonic time because of this reason. And the reason could be taken from the error no, right? And then we crash the entire thing. There we go. So when we end the clock, we're doing the same thing, but for the end. And now we need to find the difference between end and begin, right? So, and let me take a look at the definition of this specific struct. So, time spec, is it defined somewhere within this man page? Oh, okay, so here is the definition of the time spec. All right, that's pretty cool, isn't it? I think that's pretty cool. So we have seconds and all of a sudden nanoseconds, not milliseconds, not microseconds, nanoseconds. That's how precise that shit is. Look at the resolution we can work with. Isn't that amazing? So resolution is nanoseconds. Wow. So milliseconds is 1,000. Microseconds is million, right? So it's a million. Nanosecond is billion. So that's how 1 billionth. Is it? I think it's 1 billionth. Nanosecond. 2 to the power of 8, right? So we have 8 zeros. 2 to the power of 8. Yeah, to the power of -8. Okay, so that makes sense. All right. So that's cool. That's a pretty poog resolution, not gonna lie. So let's calculate the elapsed time. Elapsed time. So we're gonna measure it in seconds. So I think double is gonna be big enough to actually take into account such, you know, such a fine resolution. So we're gonna do end TV sec minus begin TV sec. And also we're going to add the same thing, right? We're gonna add the same thing, but TV and sec. But we also need to divide it by 10 to the power of, yeah, we can actually multiply it by 1 minus, I think that's how you can do that, right? Is that how you can do that? I think this is the way to do that. And that will give us the right thing, hopefully. Hello, Zolder Sir Twitch, welcome, welcome, welcome. So this is the elapsed time, I think. And then we can say something like elapsed time. Clock elapsed time is going to be LF6 elapsed. There we go. Cool. So yeah, that's two functions, right? So we extracted all of that. So now if I want to measure time, the only thing I have to do is just like begin clock, right? Begin clock. And then end clock. There we go. And I don't have to do anything else. So and it's going to be the same in the single threaded mode as well. So yesu, kawaii freaking desu. Begin clock. So this is the begin clock, and then we're gonna end the clock. All right. So maybe I'm gonna actually, well, I mean, to do is should be in a single threaded version. So maybe I'm gonna disable the threaded version, right, and just see how single threaded performs. Clock get, oh, wait a second, clock get time. Emacs, the fuck was that? So we already include time. I think that's what we need to have here, right? Emacs. Real voice, real, yes. It's my voice changer broke for a second. You could hear my real voice. So, yeah, we need to enable this shit. IMAX, yes. 1993. 09. Is that like a date? I think this is a date. Interesting. Let's define this macro. I think you have to define this kind of macros like at the beginning of the source, if I remember correctly. Right. So that's the Posix we are using. Is this portable enough? Is this portable enough? Hopefully it is portable enough. All right. So now I'm gonna try to do a compilation of our nation, and oh, this is a clock. TP end and TP begin. TP end, TP begin. There we go. So end, not two. TP, please. The fuck? TP. And we have to also do it in the CD error. Finally. Okay, so it's doing the thing. So it's supposed to be like 10 seconds, if I understand correctly, right? It's supposed to be 10. Maybe I should actually reduce the size of the tile. Okay, so that kind of worked, I think. We cannot see the nanoseconds though. We only can see milliseconds. So this could be due to the printf, actually. This could be due to printf. So what if we increase? Oh yeah, this was actually a pretty good idea to actually extract all of that to separate functions, because now I can modify this thing in a single place and not worry to copy paste thing around. Right. So let's actually say that we're gonna have 9 zeros after the period, right? So because I want to see those juicy nanoseconds, even though maybe double won't be able to represent, but double should be able to represent them. Double has a huge precision. So yeah, so I want to see those juicy nanoseconds. Show me them. Time before January 1970. Well, time didn't exist, so basically. Okay, so I can see them juicy nanoseconds. Nice. That's pretty good. Even though it's probably useless for me, because I'm looking for like a magnitudes improvement on the performance, right? At least one magnitude, right? So now let's go to the threaded and let's see how the multi-threaded version performs. Will the multi-threaded version perform faster? So here's the multi-threaded version, and so the previous one was 12 seconds. So this one is going to take 7 seconds. Well, yeah, there we go. One magnitude, basically. Not bad at all. So. I think the difference is going to be even bigger on huger tiles. So you know, I'm going to actually disable the saving to PNG because it takes too much time, right? So we want to stop the execution as soon as it, you know, finish the rendering, right? So just basically render it into memory and forget about it. Yeah, so this is basically 5 seconds. And if we need to compare those things side by side. You know what I'm talking about? I think I want to be able to compare them side by side. That would be actually kind of poug. So let me modify my build tool. So here, I want to have a special subcommand, right? If strcmp. So this is going to be a temporary subcommand specifically to bench multi-threaded execution. So 1.3 little dual core, yeah, probably. So I wonder if the amount of threads will change something. Maybe, I don't know. So if you want to have less amount of threads, you need to do more organization. It's just easier to create like a thread per tile, and we're not gonna have probably more than 16 tiles anyway, right? Because the full Wank tile set is precisely 16 for 2 colors. I don't want to go into multicolor, you know, stuff like 3 colors or 4 colors, because that greatly complicates the Wank tiling algorithms and stuff like that. So yeah, I'm probably not going to do more than 16. But we're definitely going to do multi-threading for generating the final grid, because in the final grid we're copying from the atlas into the other thing and matching the corresponding sites. So that's also going to be multi-threaded. I think there we're going to do some organization work. Okay, so what I want to do, I need to come up with the subcommand. Multiple Wanks at the same time, yeah. So maybe I could call it bench, I don't know. What would be the good name to actually call such subcommand? Thread, because I want to just check threads, right? So let's actually call it thread. So, and in here I need to actually build 2 executables. First executable is going to be Wang, I suppose, single threaded. So let's call it ST. So this is a single threaded, and the second one is going to be multi-threaded. And for the multi-threaded, we're going to enable threaded. There we go. So this is going to be something like that. So we have a single threaded and multi-threaded. So we already built a single threaded version once. So maybe I'm going to do the following trick. So I'm going to only build the usual stuff for these subcommands. But when you do thread, we actually build a different set of subcommands. I think that's the trick we're gonna do in here. If we don't provide anything, we just build the regular thing. Alright, so once we build the single-threaded and multi-threaded, we're gonna be just running them, I suppose. I'm gonna just run cc, actually not, it's gonna be wang st and then empty. So we're gonna compare them side by side. Maybe I'm gonna actually run it right away after it compiled, so we can see a better log. And also, maybe I also want to save their state. Maybe I want to save their state to actually compare the resulting files, but we can do that a little bit later, right? Okay, because right now I want to compare the performance on like big tiles, like 4,000 or something. All right, so let's do thread, right? And unknown command thread, really? Did it not rebuild itself? I asked specifically for this thing to rebuild itself, but it didn't. Oh yeah, I see what's going on. Yeah, classic. Classic. All right, so it seems to be working. Okay, so we compile an ST, and oh shit. Okay, that's wrong. So we need to disable that thing. If we're passing this, we're already passing this macro via dthreaded, so we don't have to do that in the source code itself, right? The build system provides that thing for us. We don't even have to think about it. Is this style rendering of yours consequently renders different chunks of the image so the threads are not concurrent, or do I misunderstand? You misunderstand. It does them in parallel. Okay, so the single-threaded one is 9 seconds, the multi-threaded one is 6 seconds. Okay, so now let's increase this entire thing. Who needs a makefile? Well, yeah, we're using a build system called NoBuild. Right, so this is a NoBuild build system. If you never heard about this build system, I actually recommend to check it out. It's actually pretty cool. Right, so essentially the idea is that it's a header-only library for writing build recipes in C, and you can just invoke external commands. And you know what's cool is that these sort of things are cross-platform. So you can easily write a code that can also compile and work on Windows and also with Microsoft Visual Studio in a similar way. So this entire script itself is not really cross-platform because we're directly calling to Posix stuff, but you can make it cross-platform. So when compiled with different compilers and different operating systems, it's going to actually work differently. What's the point? If OpenGL renders, we're not using OpenGL. Alright, so 496, there we go. So let's actually compare the performance on the bigger tiles, single-threaded ones. So I wonder how much time it will take. Also, I'm also streaming, so it's probably going to be slower if I didn't stream. Alright. That's a lot of time, actually. Okay, it's almost a minute. So for a single thread, 4K by 4K took 42 seconds. Let's see how much time it will take for a multi-threaded one. So it should probably take 20 seconds then, right? Or maybe, I don't know, 25, something. Alright, it's 20 seconds, alright, so that's pretty cool. Okay, so now let's compare their output results. So 256, there we go. So, and what I want you to do actually, I want you to enable the saving to the file so we can actually compare this stuff. So I'm going to enable it like that, and this is going to be output file path. Right, so this is a threaded one, so it's going to be empty. And in here, we're going to have st, right? With sta, st. So, and let's just go ahead and see how it's going to work. Okay. All right. So that's the final result. So, and we have two outputs. So this is a single threaded output. right? This is a single-threaded output, and this is a multi-threaded one. They're identical. I don't see any differences between them, at least with my naked eyes. Right, so, yep, looks fine to me. So I guess that's how you would parallelize the atlas rendering. So it's pretty poke, isn't it? I think it's pretty poke. We can just keep it by default, right? So, and every time we need to regenerate the atlas, maybe we can just call that thing. So another interesting thing, like we have this stuff that allows you to measure time. I want to be able to disable and enable like these time measurements, right? Depending on some sort of like a compile time option. So maybe I'm gonna go ahead and extract the you know, clock thingy to a separate unit. So let me see. So how should we call that that unit that measures the time? Prof? We can call it prof. I don't know. I'm not sure if that's a good idea generally, but yeah, whatever. So this entire thing will probably need time, and I'm going to copy paste the entire thing in there. Right, there we go. And we're going to be just including the prof in here, right? So, and when I have like some sort of compile time option, right? Some sort of compile time option. How that option is going to work? So if you have defined some sort of like a profiling, right? So I don't know. It's gonna include this kind of stuff. Otherwise, we're going to have like empty macros in here. So something like this, and I suppose we can say define, and for these things they're gonna be absolutely empty, hopefully. Yep. So that way we can just completely disable them and remove them from the code if we don't want those things. But to be fair, I'm not sure if we want them or don't want them. I don't know. All right. So if I try to run this this kind of stuff now, okay, definitely define. All right. So what do we have? So yeah, it didn't have any profiling, as you can see, but specifically for this like threading bench, right? Where is NoBuild? Where is NoBuild? I don't see the NoBuild. Right, specifically for this kind of stuff, we may enable the profiling, the prof, right? Yep. So, and let's just, that will automatically work, hopefully. So it's taking some time. There we go. You know, you may have actually several like time measurements, and if it just prints clock elapsed time, it's really difficult to understand what exactly happened. Maybe we want to extend the interface of our like prof thingy to also accept some sort of a message like this, or maybe some sort of a label, well, let's call it a label, that will be printing along when you call end clock. You know what I'm talking about? So when you take the actual measurement, when you print the actual measurement, it will tell you what exactly your measurement if we have several of those things, right? Also, you cannot have nested of these things. And I'm not sure if I want to have nested all these things. If we want to have nested measurements, we'll probably have to organize some sort of a stack, which could be also an interesting idea if we actually need that, but I don't know. So I guess for now, so you can't have nested. So yeah, let's actually do something like this. This is going to be... since everything is prefixed with TP, I don't know, maybe I'm gonna call TP label. Why not? Right. So, and here we get the time, and we also set a TP label. See, global variables make programming way easier. Time seconds on, and maybe we can actually put the label. I don't know, somewhere here maybe. So it's gonna be something like S label. There we go. So, and well, here you'll have to specify the label. I think the easiest way to do in here would be to just use variadics, I think. Right, so yeah, you don't care. So you can provide any arguments, how many arguments you want, and it will just ignore all of them, so it doesn't fucking matter. So that's just like makes it easier to disable this entire shit completely. All right, so, and in here, when I do begin clock, I'm gonna say Atlas, right? So this is the Atlas generation, Atlas gen, maybe, I don't know. And here we also have an Atlas, Atlas gen, right? Let's see, and label, it's a TP label, okay. Yeah, so Atlas gen, there we go. So we can clearly see that this is the thing that we have. It's like two time improvement. And I don't know if I want to have this kind of thing, you know, enabled by default. I think I want to keep it enabled by default because I think it's kind of cool, isn't it? I think it's kind of cool. So maybe we could extract the whole process into a separate function that would be called, you know, generate Atlas, right? Atlas, right? And we can move the entire stuff here. So we are generating Atlas. Generate Atlas. There we go. And let's try to recompile the entire thing. So output file path. So that one is interesting. So depending on the threading, we also have to pick different things. I see how it is. I see how it is. So that means somewhere here we'll have to maybe do something like output. So I'm gonna just remove that thing. Then we're gonna remove that thing. Also, maybe I'm gonna move the printing of this stuff here. Multi-threaded. Okay, so here's the multi-threaded, and I'm gonna put this entire thing in here before generate Atlas. And in generating the Atlas, we're not gonna have any of these like things that are not important. No, none of this stuff is really important. Maybe we can clock the whole thing then, right? So maybe we can even move clocking of this stuff like here now, right? Since we moved everything away. Generate Atlas, there we go. So we remove that, and yep, so here's a threaded, multi-threaded, and a single-threaded. Hello XT Cello, welcome to the stream. How are you doing? How are you doing? So yeah, this is actually pretty simple. Generate Atlas, multi-threaded one is just like creates pthread, single-threaded one just does that within a single thread. Maybe we can even reuse this function for single-threaded one. It's just like call to this function. I don't know, so it will be rather interesting. But I still cannot decide if I want to leave it as a compile time option or as, you know, basically always use multi-threaded approach. Because if I'm gonna have an option to switch between single-threaded and multi-threaded, it will add a lot of complexity, right? So that now I'll have to always think like, here's the when I'm gonna be generating the final grid, right? So do I also want to have a single-threaded version of grid generation or multi-threaded version? So I think it would be easier to have like always multi-threaded version and maybe put something like a limitation on how many threads you can create per thing. So yeah, I don't know. So maybe I need to think about that. Cool. So let me try to run this thing one more time. And maybe we're gonna do a committee. So there we go. I think I'm gonna include only that stuff, and that stuff. And yeah, let's do something like implement the multi-threaded prototype of Atlas generator, right? So, and I'm gonna push that right as a repo, and let's make a small break. And on the break, I'll make a cup of tea, and I will think if I wanna have a compiled time option to enable threading or not. But so far, I'm thinking about just always do multi-threading and maybe have a compile time option for how many threads, like what's the size of the thread pool. But if we're gonna have a size of the thread pool, we need to organize the thread pool and whatnot. So, we'll see. The winner gets tea, that's for sure. All right, so yeah, let's make a break. All right, so I made a decision. So let's actually only use multi-threaded version, right? So let's completely remove all of that, and we're only gonna have this stuff. So there's not gonna be two separate modes. It's always gonna be multi-threaded, but we're gonna put it to do. A runtime parameter to limit the amount of created threads. Right, so yeah, basically maybe we want to have something like wang j5, like similar to how you do that in make files, right? So you can do usually make j5 or 6 or so on and so forth, and it will basically create no more than this amount of separate processes or something like that. So we want to kind of do a similar thing, but I'm not going to not going to be working on it right now. So I'm going to just put it to do and forget about it successfully. All right. So yesu kawaii desu. Okay. So let me also remove the code in the build system. We definitely don't need this kind of stuff anymore, right? Definitely don't need it. So maybe I'm going to actually keep the profiling enabled all the time, just so we see how much time it takes for the for the Atlas generation to work. So because we're gonna move on to a grid generation, right? So once we generated an Atlas, now we want to define an arbitrary size grid and then fill it up with wang tiles and render this entire thing and also save it. So we want to be able to profile like several steps. Okay, so here is the Atlas generation, then we're gonna have grid generation, and maybe we can also time the PNG generation, why not? So we can do something like begin clock, PNG out, right, and then it's going to be end clock, right? So we can basically clock each individual phase. First Atlas, then PNG out, and also grid, and so on and so on and so forth. That's actually pretty cool. Yep. So yeah, creating PNG took longer than creating an Atlas, right? Because I presume write STB image write does the compression and so on and so forth, right? So it's probably more like labor intensive than just generating some gradients and whatnot, right? So that's why it takes a little bit more time. Yeah, that's understandable. That is perfectly understandable, but this is just an output, right? So it's not really part of our algorithm or anything like that. Okay. So let's remove that, and okay. So I also probably want to go to delete trailing white spaces. Okay, remove single-threaded version and use multi-threaded by default. Hamikovi, thank you so much for 17.
prime number.
It is in fact prime number, isn't it? Yes, it is prime number. Thank you so much for the 17 months of tier 1 subscription. 1 is also prime number, isn't it? No, it's not prime number. Thank you so much for 17 months of tier 1 subscription and welcome to our epic prime number club. Yes. Who knows why 1 is not a prime number? Well, I mean, it's not a prime number by the definition of prime number. I really like the definition of prime numbers, by the way. It's really cool definition, not hackish at all. So the definition of prime number is any positive number, right, that is divisible by 1 and itself, except 1. So essentially, the definition defines an infinite countable set, right? It just defines a set and punches a hole in that set. So it's just so funny, like, yeah. So I absolutely love it. 0 is not a positive number. So it's actually kind of cool. It's like a positive number, right, that is divisible by 1 and itself, except 1, right? So here's the set, but except that thing, except that thing. So it's just like I always find it funny because usually a majority of the mathematical definitions that I find, they're not this hackish. So which makes sense. I mean, why not? Why can't you define a set and then punch a hole in that set? Why not? So I don't see any problem with that. That's just like kind of fun. Anyway, so the next thing we're going to be doing, we're going to be finally generating the Wang tile grid. A Wang tile grid. So to do that, we need to define the size of the Wang tile grid in tiles themselves, right? So we have a convention in here that if your constant has a tiles measure unit, right, it has to be suffixed with TL. If it's pixels, it has to be suffixed with PX. So and that is needed to not confuse them around because that's quite important. All right, so let's define grid width in tiles. And let's actually generate a pretty small grid. Let's generate like 5 by 5 grid, right? And we also need to be able to allocate the display for the grid where we're going to be putting actual pixels of that grid, right? So, and for that, we'll have to define constants something like grid width in pixels, which is essentially taking the grid width in tiles and multiplying it by tile width in pixels, right? So you see, you have to be super careful with measure units in here, and especially when you use them to allocate memory and whatnot. If you use the wrong measure units, you're gonna have a buffer overflows and whatnot. And I should stop saying and whatnot too many times. But I haven't slept like long enough today, so I think I'm allowed to actually say weird things. Okay, I'm gonna replace width with height, right? So there we go. So we have a grid width and height in tiles and in pixels. All right. So and we need to define two buffers in here. The first buffer is going to contain the BLTRs of the grid. And if you followed the series correctly, you know that BLTR was open README because everything is documented in README, right? So BLTR is a 4-bit mask encoding the specific Wang tile. Each bit represents a side of the tile in the following order: bottom, left, top, right, and that's why it is called BLTR. Not because it stands for bacon, lettuce, tomato, and ranch. No. It stands for bottom, left, top, and right. So it's not a sandwich. It's a mask. So a 0 in that mask means the first color, and 1 means the second color. Since we're working with the two colored wank tiles, we have only two colors. So 0 is one color, and 1 is another one. So, and whatever is going to be that color, it's up to you. In our case, we just assigned, you know, 0 to yellow and 1 to blue, right? And that's how the wank tile set looks like right now. Right, so a single tile is actually this, and as you can see, each side of that tile has either blue color or yellow color, right? So, and specific artistic style of the tile could be different. The only thing that is important is the color of the side and how the different sides match together. Right, so if we want to generate a random wank tile grid, right, we need to allocate an array of those BLTRs, right? So, and let's call it something like grid. And the size of this thing is going to be grid width in tiles multiplied by grid height in tiles. Right, so first we need to generate this array, maintaining the constraints of the tiles, right? Is the color on the side of the tile basically defines a constraint, what kind of other tile you can put in there, like in a game of domino, right? So it's almost like playing a game of domino. Then once we've got this thing, we need to have we need to fill up the buffer of pixels, right? Grid, let's call it grid image, right? And the size of that buffer of pixels is going to be grid width, but in pixels already multiplied by grid height in pixels. So this is the actual tiles that we're going to generate, and this is essentially the thing that we want to save to the hard drive, right, to display. So this is the display, the actual image, the actual pixels. So, and the way we're going to do that, so each corresponding tile within this array is going to be indexed in a lookup table in the atlas, and then once we find that specific tile in the atlas, we're going to copy it in a corresponding position within the grid image. And this process of actually rendering the wank tile grid could be also parallelized. We can try to parallelize copying chunks of data into the final image. I wonder if it's going to make it faster, because I don't know if it makes sense to parallelize copy in memory when you're not doing any processing. Maybe it does make sense. We're about to find out. In any case, we're about to learn something interesting, right? Either it does or either it doesn't, right? So, cheers. Hi again. Hello, CyberSecLong. Hi again. All right, so let's go. We're gonna have begin clock, maybe grid again, begin actually end clock. So, and maybe we're gonna actually have two phases. We can try to split that into two phases. So we could have grid generation and grid rendering. That's kind of interesting. So just to see, like, you know, which phase is the you know, slowest one, rendering. So, and technically, this part is atlas rendering, right? So here's atlas rendering, grid generation, grid rendering, PNG output, and there we go. There we go. So grid generation is rather interesting. So let's try to draw a grid of tiles, right? So here's one thing, then here is the single tile, right? And then here's another one. So one thing I probably want to do, I want to actually maybe generate a couple of these things, right? And then I can generate a couple of these things. There we go. So, and this entire thing sort of continues in all of the directions, right? So let's actually remove this kind of stuff to indicate that it's gonna continue. Boom, there we go. It continues in all the directions. So, what's cool about this stuff, about this specific corner, right, is that there is no limitations on that corner whatsoever. You can place whatever mask you want in there, right? Literally one of the 16 things. There is no limitations. For this row, there is always left limitations. Each individual tile in here is limited by its left tile, right? So each of these things have a left limitation, right? So here's the left limitation. This column is very similar, right? It's limited by top tiles, right? So, and the rest of the tiles are limited by both top and the left, right? TL, 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 TL. So yeah, there's only 1, 2, 3, 4 situations that you have to take into account. All right, so, but originally I wanted to basically have a generator that doesn't really care about specific cases and can handle whatever case you want, right? I just want to be able to say the following things. So I want to be able to generate like a random tile, and to that generator I want to be able to say, okay, so here are the bits of the tile. So where you have a dash, you can put whatever bit you want, but in that specific bit you have to have this value, and in that specific bit you have to have this value. So, and for the rest of the bits, do whatever you want, right? For the rest of the bits, do whatever you want. I want to have this kind of function where I could tell, okay, here is the description of the constraints, and given these constraints, give me a random tile that satisfies these constraints. Right, so this is what I want to be able to do. Make sense? That would be kind of cool. And that way, as I iterate through the tiles, I would look at their like a top and left tiles, then build this constraint description and just give it to this function, and it will give me the next tile, the next random tile. Right, so but the question is, how can you describe this kind of, you know, constraints? Right, you cannot just give a single mask, right? Because you don't know, okay, so when I have 0 in here, do I mean that I don't care about the bit? Or do I mean that I care about the bit and I want it to be specifically 0? What exactly do I mean by 0 and what exactly do I mean by 1? So with a single mask, it's almost, I think it's not even possible to describe the constraints. Right, so, and what originally I wanted to have, I wanted to have 2 masks, right? The first mask is basically a value mask that contains the specific values that I care about. And the second mask is a position mask that contains what are the things that are fixed, right? So the bits that are equal to 0, I don't care about them. The bits that are equal to 1, I do care about them. So, and essentially, if I combine these 2 masks together with a conjunction, right, so I take A, B, C, and this thing, I'm going to end up with 0, B, 0, D. There we go. So the constraint, oh my god, the constraints are described by 2 masks, the value mask and the position mask, and then if I combine them together, I can see what kind of bits are expected in here. So, and now let's say that I want to answer a simple question. Given constraints V and P, if I have the tile C that has values X, Y, Z, W, how do I know that this tile fits the constraints defined by these 2 masks? Well, if I take the tile and also apply the position mask to it, right, what I will get is 0Y, 0W. So the way I can see if this C fits the constraints, I can just compare this entire thing to this entire thing, right? So basically, I just need to compare if these 2 values are equal. you invert the mask because you need the right edge when choosing the left tile index. The rest is random ordered. What? I don't know what you're saying. Okay, so this is how I check for the constraints, right? Right, so I have a specific tile and I have a constraint description, and this is how I can answer whether the specific tile actually fits those constraints, right? I take the tile, apply the position mask, I take the value mask and apply the position mask, and if they're equal, this thing fits the constraints, right? So once I have this operation, right? Once I have this operation, how can I generate a random tile that fits the constraint? So I think the easiest, like maybe there is a smarter way to do that, but we can just generate all of the tiles, all right? And pick those that satisfy the constraint, put them into some sort of a list, and just pick a random value from that list. So I think this is going to be the easiest way to do that. And since we have a constant amount of these tiles, this is going to be O of 1 anyway, right? If n is equal to the amount of tiles in a grid, right? So this is going to be pretty much constant relative to that specifically, right? You see what I'm talking about? Then just brute force C. There we go. So we can also do something like fits, right? And here we're gonna accept VPC. This is how we do that. Just brute force C. Checking if it fits the constraints VP. There we go. So does this make sense? I think it does make sense. I was thinking about better solutions on how to generate a random tile based on the constraint description. This is the best thing I can come up with, but I'm actually a pretty dumb person, so maybe you can come up with something better. Right, so, and it's also pretty fast, like you just do 15 iterations and that's it. Right, and each iteration is just like a bunch of, you know, bit mask operations. So, know what I'm talking about? So, let's implement random tile then. So maybe I'm gonna actually move this entire thing somewhere up there. Maybe. So this is related specifically to rand tile, right? So let's do BLTR rand tile, all right, and in here we're gonna accept the mask of V, all right, so here's V and UAT P. Well, maybe since they also keep the bits in this specific order, we can also call them BLTR, why not? And also here's the interesting thing, each mask is 4 bits. Can we actually combine both of the masks into a single byte, if you know what I'm talking about? Can we combine them? That's actually a very interesting idea. Just have a single description. Okay, so essentially, I didn't think about that. So you can also say that VP is ABCD 0101, right? So here's that. And how do you check constraints? Okay, so maybe I'm gonna actually put it here to sort of like underline everything in here. So I'm gonna actually put this here. How do you check that you fit a particular constraint? So you can do something like C, and in this case you need P, right? In this case you need P. This is actually very cool. So that means, okay, so the P is going to be VP 0B 111. Right, and what is this value? I actually forgot. So 15. Okay, so that means we can do something like, I'm gonna actually keep it like this. Right, so this takes that, and that basically this is rather interesting. Okay, so we can actually go even further and say that this is going to be XYZW, right? XYZW, right? And essentially, if we apply C to VP, what we're going to end up with, right? We're going to end up with 0, 0, 0, 0. Right, so here is the edge. We can also put the edge somewhere here, right? So here's the, like, you know, the nibbles, right? So I think they're called nibbles. Here's going to be 0, then Y, then 0, then W. So this is what we have in here, right? And then if we take VP and shift it to 4, we're going to end up with just 0, 0, 0, A, B, C, D. And here is the interesting part. What if in the constraint, so here we just need to apply the position mask back to the value mask. But what if we pre-apply it? So originally it's going to be just this. So that means, right, that means in here you will just have that, right, you will have just that, and the check is going to be essentially C and VP, whether it's equal to VP 4, right? And that way you can pass only one thing in there. Is it worth it even? I don't know. It's actually rather interesting. It's rather interesting. So interestingly, can we get it even further? Is it even worth it? Because it's not really simplifying anything. You still do 2 operations, like here you do 2-bit operations, and here you do 2-bit operations, but then now to use rentile, you have to do more work to pack all of these bits. So yeah, I don't think it's worth it. I actually don't think it's worth it. Because in this particular case, you don't really need to pack anything, right? You just need to know what the values are and what their positions are, and that's it. So yeah, so because that doesn't change anything, that doesn't introduce any, like, it doesn't add any value to the situation whatsoever, so screw that. But that was interesting, you know, thought experiment, right? So we're gonna have 2 parameters instead. 2 parameters. Okay, good. So we're gonna have some sort of candidates in here. So it's gonna be BLTR, CS, and we're gonna have like 16 of them. So all of them are filled with 0, and also we're gonna have N, which indicates how many of them we have. Right, so we're iterating each individual candidate starting from 0 to less than 16, right, plus C. And if CP is equal to VP, right, something like this, we're going to be adding that candidate to the list. There we go. And after that, we're just returning that candidate, like a random candidate from the list. That's it. That's the entire generator. So having the constraints, we just generate a list of the candidates, and we just pick a random element from that candidate. Easy peasy, lemon squeezy. Cool. So yeah, that's definitely simpler than, you know, going through a single parameter. Right. So let's actually give some sort of like names in here. So this is the value mask, position mask, candidate tile. Right. All right. Cool. Let's see if this entire thing even compiles. So I'm gonna just do build. Is it compiled? Is it compiled? Seems like it's compiled. Cool. So now we need to start doing this kind of stuff. So we want to generate the first ever tile that doesn't have any limitation, right? So if I have random tile, there we go. Right. How do I indicate that it has no limitations? Well, I can say, I can actually put whatever I want in here, right? Maybe 69. And I'm just saying that none of the positions here matter. That's it. So this thing doesn't really matter. But I mean, for the cleanness, we can put 0, 0, and that means it will generate a random tile without any constraints. So it will put whatever in there. So, and we need to put that into the grid. So, and the first tile, the left top tile, is basically 0. I think it is. So yeah, there we go. So get that. So maybe we can take a look at how it looks like in the debugger. I don't know, just in case, just to see what kind of tile got generated. But after we generated the first one, I think I want to generate the first like row, right? The first row. Then we can try to generate the first column, and then we're gonna have like a nested loop that generates the rest of the things for the entire grid. Alright, so that looks okay, not gonna lie, I like that. Maybe I'm gonna take a look at that in the debugger just in case. Alright, so I'm gonna go to the TeamUX, I'm gonna cd in here, and then I'm gonna have NoBuild GDB, break main, boom, 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 boom. Okay, then I'm gonna run this entire thing, and there we go, so we have that. So we generated the, oh, that's actually pretty cool, look at that, it just generated, yeah. So I forgot that GDB actually keeps track of threads and stuff like that. That's pretty funny. Didn't expect that. Okay, so it took this amount of seconds. Anyway, so maybe we can try to display the grid, right? So now it's filled with zeros, but after we, you know, generated a first tile, now it's equal to this, and it interpreted as an ASCII, which is kind of dumb. So can I just, yeah, so there we go. So it's a 7, which does look like a tile. So it's not bigger than 16. So yeah, we generated the first tile. Isn't it POW? I think it's pretty POW. Okay, let's go ahead and generate the first row in here. So we're gonna be generating, like, I suppose X, right? But the X0 is already generated, so we're starting iterating from 1, right? So X less than grid width in tiles, not in pixels. It's quite important. It's in tiles because we're doing the tiles. Okay, so the next thing, we now need to generate the tiles as following. Oh boy, since we are on the first row, right, so we usually, how do we determine the rows? So it's usually y multiplied by grid width plus x. But in our case, y is 0, so this entire thing cancels out. So we can just generate things like this, I suppose. Alright, so we're generating a random tile. We don't know what's going to be the value mask, but we already know the position mask. We only care about the right element, about the left bit, right? So since we have BLTR, so the only thing we care about is this bit. So that means the position mask should be something like this, which I can probably generate by taking 1 and shifting it to the left 2 bytes, right? So in this particular case, it's going to be something like this, right? So this is equal to that, this is equal to that, 0b, and the position mask has to be equal to that. So I'm going to just assign it like this. There we go. What's going to be the value? What's going to be the value? Well, we need to take a look at the previous style, right? We need to take a look at the previous style, and what do we have in the previous style? Right, so here are the bits, here's BLTR. We need to take the right bit of the previous tile and move that bit to the left position. That's what we need to do. So that means we will have to okay, it's already right. So what I need to do in here, I just need to do 001, right? I just need to do 001, which will give me let's actually do it like this. 001 0b. So I just want to keep everything consistent, right? So, and this will give me only this thing. There we go. And after that, I need to move the entire thing to 2 bits, right? I need to move it 2 bits to the left, right? So I'm taking the right bit and I'm moving it to the position of the left bit, saying that okay, left bit has to be equal to that. So that's basically what we're doing. So in a binary, right, this thing is going to be equal to just 1, right? So that means the actual thing in here is going to be equal to 1, 0, 2. Maybe we can also do something like value, right? So here's the value, it's going to be like this. And the position mask is going to be like this. There we go. So, and we generated the entire thing. Cool. Pretty cool. Pretty cool. So let's try to see if it actually generated anything in the debugger. You know what would be cooler? It would be cool to implement the grid generation and grid rendering simultaneously. So as we implement more and more rows, we'll be able to actually see if they got generated correctly. You know what I'm talking about? Right, so after we generated the first row, we can just go ahead and try to render that row, right? And then save it to the output and just instantly see if we got it correctly. So there's no need to guess on see in the debugger or anything, but we're still gonna look in the debugger just in case, you know? Just in case. All right, so I'm gonna break somewhere at 222, I suppose. So I'm gonna be main.c222, and I'm gonna just run this entire thing. All right, so I'm gonna go in here and let's take a look at the grid. There we go. So that gave us a bunch of things in here. So the size of the grid, is 5. So we have 1, 2, 3, 4, 5, and the rest is 0. Right. Okay. So we generated the first row. So here are BLTRs, the masks of the first row. Does it make sense? I think it does make sense. Okay, the next thing we want to do, we want to basically render the entire grid. Right. We want to render the entire grid. How are we going to be rendering the entire grid? I suppose we're going to be just iterating each individual tile of the grid and knowing the BLTRs of those tiles, right? So we know BLTRs of the tiles. We can use these BLTRs to find that tile in the atlas, right? Where's the atlas? In the atlas, and copy the corresponding chunk from the atlas into the grid image, right? So atlas acts like a hash table, and the BLTR within this thing like a key within this hash table. You see what I'm talking about? Right. So yeah, this entire thing is basically the hash table. Valid 0, thank you so much. Thank you so much for 2 years. Holy fucking shit. Thank you for 2 years of tier 1 subscription. And welcome to our Epic Renderers Club. How about that? How about that? Isn't that epic? I think it's goddamn fucking epic. Alright, so that's pretty interesting. So yeah, it's actually, I really like how all of these pieces like fit together really nicely. Right, you have very well distinct phases that are easy to parallelize, except maybe grid generation. the grid generation is not parallelizable because, as you can see, each cell depends on previous cells, so you just cannot parallelize this process whatsoever. But luckily, this entire thing is actually quite fast, right? So it's just like a bunch of bit operations, nothing super special. We're not doing any mathematical operations like sine, cosine, or whatever. So it's just like a messing with bits, and you can just generate that pretty cheaply, I think. So, and here we just copy in the memory, right? I think the heaviest operation is generating the atlas, because in generating the atlas, we have to actually do mathematical operations like sine, well, not really sine cosine, but you know, f-mean and lerp and what the actual math with floating points and whatnot. So yeah, so the rest of the stuff is probably not that intensive. Anyway, so let's do the rendering. Let's start iterating. So I'm going to be iterating from 0 to you know, grid tile grid. We actually height in tiles. It's quite important. We're iterating the tiles of the grid. Then we're going to be iterating the columns of the grid. So this is going to be something like this: column grid width plus x, and there we go. So within this thing, we can extract the BLTR. So this is going to be y multiplied by grid height TL plus x. There we go. We have a BLTR which defines the atlas position, right? Which defines the atlas position. And the question is, how are we going to be finding that atlas position? So there is a couple of serious measure unit transitions here. So here we're using tiles. Then we need to figure out the tiles within the atlas, right? Within the atlas. Then we need to transition those things into pixels. So I think we need to actually prefix, like suffix this thing with TL, indicating that we're iterating specifically tiles. Right, so here are the tiles. And those are the tiles of specifically grid, right? So these are the tiles of grid, so it's going to be GYTL. So G stands for the grid and TL stands for the tiles. So we encode a measure unit in here. And here we also have the G. Okay, so BLTR gives us the position within the atlas, also in tiles, right? So it's going to be size T. So atlas is going to be A, Y in tiles. So A stands for the atlas. So we take BLTR. So a row is basically BLTR divided by this the size of the row of the atlas, which is the width, right? The width. So it's going to be atlas tiles, atlas width and tiles. Yeah, it's atlas width and tiles that gives us this specific row, and specific column is mod of this thing. There we go. So we have AX in tiles and AY in tiles. All right. So that's pretty cool, you know. But now we need to actually convert all of these coordinates to pixels, because we want to know precisely you know, the positions within displays and whatnot. Right, so what I have to do now, I need to take GYTL and GXTL and convert them into GYPX and GXPX to the pixels. Right, so I'm gonna do something like this. Maybe GXTL PX, right? GXTL multiplied by the tile width in pixels. So this is how we convert that to pixels. Then GYPX is going to be GY tiles, tile height in pixels. There we go. So we converted these coordinates from tiles to pixels. Now we want to do the same for the atlas coordinates, right? We want to do the same for the atlas coordinates. So AXPX is AXTL, again multiplied by this thing, tile width. then AYPX is AYTL, a tile height in pixels. There we go. So we have now the coordinates in pixels. Cool. So this is from where in the atlas we have to start copying bits, and this is where this is the destination where we have to copy them. This is the coordinates of the source, and these are coordinates of the destination, right? So we need to take pixels from here, starting from here, and start copying them here. Cool. From atlas to grid. From atlas to grid. So I think I want to make some sort of auxiliary function that can copy pixels from one region of memory to another one. So I'm going to literally call it copy pixels, I suppose. Copy pixels 32. So, and here's an interesting thing. I think I need to draw this, right? So let me grab my thingy-majingy. Let me grab my thingy-majingy. Okay, so what is that? What's this over? So imagine that we have an atlas in here. So here's an atlas. So here's the atlas, and here we're gonna have the grid, which is probably gonna be a little bit brighter. Grid. So the atlas looks like this. Here is the atlas, and here is some sort of a grid. So by doing all of that stuff, we have these coordinates. We identified what tile we need to copy within the atlas and where we have to copy it. Right. So we have to perform a copy from here to here. Right. And you also have to keep in mind, so these two regions of memory, they have different shapes, they have different width and height. Right, so this is a completely different width and height. So the width and height of this little square is actually the same, so we can keep that in mind. So, and also these things have different strides as well, right? And I actually explained how we use strides to, you know, keep to actually identify the subregion within the image. So to learn more about that, to find that explanation, I would recommend you to watch the previous episode of this Wank Tile series. I'm going to put this the link to that episode in the description. Right now we don't have it publicly available because it's not released yet. Alright, so this is a permaban. I can't even copy. Why don't we have any modes in here? Modes are asleep, so we do not approve of this vocabulary. Okay, thank you, Ice Cold Witch. By the way, did that remove the messages from the... I think that removed it. Okay. All right. So I suppose it's not on the screen anymore. Right. Cool. So you see what I'm talking about? So yeah. Let's actually implement such functions. So the function that I want to implement, is copy pixels. So it's going to accept, you know, the position from where you start, where you have to copy the pixels. So it's going to be destination. Right. So this is the pointer to the beginning of the destination. So it's going to be somewhere here. So this is DST. Right, DST. And then we also need to provide the DST stride. Right, so here's the DST stride. And the DST stride is this, DST stride. There we go. So this is the DST stride. The second thing we need to provide is src, right? And this is the pointer from where we're copying it, right? So this is src. And another thing we have to provide, we need to provide src stride. And src stride is this green line in here. So you see, we're passing the information from where to where we're copying, like starting points, and also the shape of the region of memory from where we're copying. So this is going to be src stride, right? src stride. And here's an interesting thing: width and height of these regions are the same, right? So this is width, this is height, this is width, and this is height. They're the same. So, and because of that, we're going to only pass it once, right? So we're only going to pass size t width and then size t height. So, and this should be enough to copy a tile from one sort of sheet to another sheet. Right, so we're providing the position of the destination stride, the position of the source stride, and the width and height of this entire thing, and that should be enough. Okay, so we need to implement the function that just copies pixels, and believe it or not, the whole process of rendering the grid, right? The whole process of rendering the grid is just copying pixels from one region of memory, like this one, to another one, right? From atlas to grid, from atlas to grid, from atlas to grid. Okay, so how are we going to be doing that? So we're going to be copying it row by row, essentially, right? So we need to copy it row by row. So we're gonna basically iterate while this thing is not zero, right, in a reversed order, right? And now what we need to do is we need to mem copy into DST from src, and we need to copy precisely with pixels, right? We need to copy precisely with pixels, right? So essentially we're iterating this row, right? We're iterating this row, and we're copying that row to here. Then we're going to be getting the next row here, and then we're going to be copying it in here. There we go. So we're basically copying this style row by row. Right, so, but memcopy actually accepts the size in bytes, but here we have things in pixels, so we have to multiply it by the size of uint32t. And as far as I know, I think we have an alias, yeah, we have an alias for RGBA32, so that means we can actually do something like RGBA32, right? And here is going to be the size RGBA32. There we go. So we copied one row. We just copied one row, and now we need to move to the next row. Right, for the src, how can we move to the next row? Well, we know the size of the stride, so we add the stride to the pointer, and we get the next row in here. And for the destination, we take the destination, we add this stride to this destination, it wraps around, and we get the next row. And this is how we iterate, and this is why we pass in the stride. It allows us to find the next row. Right, so, and the way we're going to do that is just DST plus DST stride, and this one is going to be just DST src. Boom, there we go. And theoretically, believe it or not, this must be the whole function. I'm not sure if it's gonna work or not, but in theory, this is a whole function that takes two sheets of tiles and the positions of the specific tile and copies one tile into another sheet from one sheet to another one. So this is the whole code that describes this entire process, theoretically. You see what I'm talking about? Right, so we're iterating rows, then we're copying just a row of specific size, and we jump into the next row using the strides. Would make any sense to parallelize that loop? Each row is copied by a different thread. I think it's too fine. I would actually parallelize copying the whole tile rather. Anyways, so that's why I found, when I was explaining the concept of stride, that's why I was so, you know, I don't even know how to call that, so surprised by it, because I would imagine the code that copies two-dimensional subarray into another two-dimensional subarray to be more complex than this. Don't you think? Like, you have a two-dimensional array, two-dimensional array, and you need to copy one subarray in two-dimensional array into another subarray of two-dimensional array. How much code do you need to do that? Two-dimensional arrays, two-dimensional subarrays, one to another. To be fair, like, I wouldn't expect this much code. Like, I would expect more code, but that's why I find the concept of stride so fascinating. You can just, like, yeah, you can compress this entire thing into just this, and this is beautiful. I'm not sure if there's any bugs in here. Maybe I just confused some measure units, right? So here we have pixels, but in memcopy you have to work on the level of bytes, right? So I always confuse those, right? And stride is usually in pixels, right? In our code base at least, right? So yeah, I hope I didn't confuse anything, but yes. Okay. So yeah, I actually spend more time explaining what this code does than rather writing this code. That's what's beautiful about it, right? So it's just like the amount of information that is compressed in this code is enormous, because I had to spend some time even explaining what the fuck this code is doing, right? So that's the level of compression this code has. So it's just like packed with information. It's also probably packed with bugs. All right, so let me see. So is this entire thing compiles? All right. So unused variable, which is fine, and it seems to be compiling. Like, it took some time to compile. I'm pretty sure it's gonna fail because it probably buffer overflowed somewhere. But we'll see. We'll see. Okay, so where is the copy pixels? Right. Cool. So what is this music playing? Oh, it's actually pretty good music. Should have listened to it. Okay, so the destination in our case is going to be the grid, right? But the question is, where in the grid? Where in the grid? I think we do know where, so it's a GY in pixels multiplied by grid width in pixels plus GX in pixels, right? So this is where we start our journey at X and Y, or by pixels. So this is where we just provide this entire thing. The stride in this particular case is the width of the grid in pixels, right? That's quite important. So here's the first parameter. So this is the destination, we're copying it into the grid. So the source is going to be the atlas. The source is going to be the atlas, but where in the atlas? Somewhere here, right? It's going to be somewhere here. So atlas Y in pixels multiplied by atlas width in pixels plus X in pixels. There we go. So, and we'll need to take the pointer to this entire thing. The stride is the whole atlas width, right? And what we're copying in here, we're copying the tile width in pixels and tile height in pixels. There we go. So this is the copy of a single tile. All right. So we're iterating through the grid. We're taking its mask. By the mask, we're determining the position of the tile within the atlas. We're converting the tile coordinates to the pixel coordinates, and using these pixel coordinates, we just copy one region of memory into another region of memory. So that theoretically should be it, I think. I think theoretically it should be, but it may fail. The next thing we need to do, so we are outputting the atlas. But now I don't really want to output the atlas, I want to output the grid. So let's actually replace this atlas bullshit. Right, atlas with grid. Ah, I should have used grid image, I just realized that. So yeah, because we have two grids in here. Yeah. So here's the first one, grid that and grid image, and this is what I basically confused in here. Why do you have extra scopes between your timer start and end? Why not? I think it looks nice. What do you think? Does it look nice? I think it looks nice. Okay. So it's sort of like determines the block, right? So we're sort of like timing this whole block. Very cool. What do you think? Just like we're timing the whole block. I don't have this scope in here, but it feels like the block is determined by the if itself, and that's why I didn't put the scope in here. But here, maybe here for 4. I mean, maybe we should be consistent, right? So maybe I'm gonna always have like this scope in here every time I'm trying to time it, and because of that, I also have to put this thing in here. So you see, I'm a little bit inconsistent with this thing. I'm a little bit inconsistent, but I think I should be consistent here. So and basically we're timing each individual phase of the generation just to, you know, keep things tight. Alright, so I'm a little bit scared to actually run this code. Well, I mean, it doesn't compile. So first we need to maybe rename some of these things. Right, I would like to call this thing something like grid TL, right? Right, because we use only tiles for this specific thing. And this may be grid pixels, right? I think it will make a little more sense. Let's actually go to the compilation errors. So this one is grid TL. This one is also grid TL. Grid TL. This one is definitely grid TL, but in here we're gonna have grid PX, right? And seems to be starting to compile. All right, so what do we do? So far, we implemented the generation of the first row of the grid, right? So we generated only the first row of the grid, and we implemented the rendering of that row. So when I run the program, what would I expect? I would expect it to exit successfully, obviously, right? And I would expect it to generate a grid of the size of 5 by 5, with the first row generated matching the constraints of the Wang tiles, right? And the rest of the rows being black, because they are not generated yet. So these are my expectations. So will it work first try or will it not work first try? I have no idea. Let's find out. Okay, so it might actually segfault, because maybe I have like a off by 1 somewhere, but we'll see. And it didn't actually segfault. Okay, so Atlas rendering took the longest, obviously. Grid generation took like, oh my god. So this is the milliseconds. 11 microseconds, right? So it took 11 microseconds to generate the first row of the grid. It's super fast operation. And grid rendering is actually also super fast. It's just copying the memory. So, and then the longest, I suppose, operation is PNG output, right? So, but we don't really care about this. So I don't really care about PNG output because it's like, you know, just debug thing. The only stages that matter in here are like Atlas generation, grid generation, and grid rendering. And the slowest among them is the Atlas rendering, which we already parallelized. So, yeah. Okay, so that should have generated us a thing, and let's open it. And that is weird. That did not do anything at all. Okay, so what's going on? Let's actually try to find out. So I was trying to save to the output file path. So an output file path is output PNG. And output PNG contains this thing. So did I put the parameters? Oh, okay. I'm still saving the atlas. I'm still saving the atlas. Maybe I could save both atlas and the grid. Let's actually save both. Why not? I mean, yeah. So atlas PNG output, right? So and the other one is going to be grid PNG output. So and in here we're going to have grid width and pixels. Then we're going to provide grid PX. And then grid width and pixels, and this has to be in byte. That's why we multiply it by RGB32. Okay, one more time. So let's see what's gonna happen. So it's compiling. All right. So and you know what? We're not using separate file names in here. So let's actually call this thing output file path. Output file path is going to be atlas PNG, right? And somewhere here we're going to have grid PNG. So I want to generate two files in here. Okay, one more time. Two separate files. It's going to be atlas PNG and grid PNG. Cool. So atlas PNG looks like as usual, and now grid PNG. As I already said, I expect only one row. Technically, it is correct. So, all right. That means my expectations were incorrect. The code works correctly, by the way. My expectations were incorrect. Since we didn't generate the rest of the rows, their values were 0. And 0 is a valid tile mask, which means that all the sides are yellow. So that's basically what happens in here. So we don't have a notion of absent tile. So if you have 0 in there, it will interpret it as the tile. It will almost look like a Ukraine flag, yes. It does almost look like a Ukraine flag. Right, so it just interpreted all the zeros as the specific tile. So, but look at that, the first row satisfies the constraints. Right, first row satisfies the constraints. So I didn't see any problems with that. So we successfully generated the first row. Yep. So that's pretty cool. We're on the right path, boys and girls. We're on the right path. So, okay, we generated this row. The next thing I want to generate this column. Oh my god. Where is my... I want to generate this column. Generating this column is almost the same as generating this row. It's just like the constraints are different and in a different direction, right? So this one is the first top left corner, right? First top row, and now we're going to be generating first left column, right? And again, we already have the first element of the column generated, so we need to iterate from 1. So the code for the first left column is basically symmetrical for the first top row, just a different orientation, right? So they're basically symmetrical. So it's going to be y1, y less than grid height, right? In TL, by the way, it has to be in TL. And what do we have in here? So we need to come up with the constraints. So we need to come up with a v, right, and p. So v is a value mask, the p is the position mask. All right, so if we take a look, the previous thing, we only interested in the previous bottom thing, right? We're only interested in its previous bottom thing. Okay, so maybe I can quickly generate the position mask. So the constraint in our case is top, right? So we're only constrained by the top. So that means top is this bit, right? That means I only need to do something like this, right? So this is the this is going to be the constraint, and there we go. We already came up with the position mask. There we go. Here's the position mask. Now we need to come up with the value mask. So we need to do something like grid. We need to fixate y. Well, it's not really a y minus 1. It's more of a y minus 1 multiplied by grid height TL. So that's what it is, right? So, yep, that's basically what it is. And its value is ABCD. So A, B, C, D, and here we have the corresponding bits, B, LTR. All right. So what I want to extract in here, I want to extract the bottom bit, right? Because the bottom bit should become the top bit, right? So let me actually do something like this. I'm gonna call this G. Right, and that way I can reduce this space in here. Yeah, there we go. So I can now, yeah, so I can just assign G. So P is that, then we have G equal to that. So, and if I apply the following mask, 0B 1000, right, it's going to be equal to A000. Right, because that's the bottom bit, right? And I want to bring that bit to the top, right? So that means I need to take this thing and move it to 1, 2, 2 times, right? 1, 2, and it became top because we're only limited by top. Okay, so, and that's basically what we're gonna have in here. So basically the value is G 15 2. G 15 2. So, and G is grid this thing. There we go. So 15, and we need to move this entire thing to 2. Okay, so we generated the first left column. Hopefully, if I didn't make any mistakes in my calculations, right? Hopefully I didn't. Hopefully I didn't. All right, so let's try to recompile the entire thing and see if I didn't. So this is a grid. It's a grid TL, right? So that's quite important. Oh, and this one is rather interesting. So it's going to be Y grid height TL. There we go. So is it compiling? Is it compiling? Okay, so if I did everything correctly, let me actually go through my logic one more time. Right, so what do we have? We only care about top bit, and the bottom of the previous one should become the top. Okay, so the position is basically the top, is just moving it to here, so that means the position bit is correct. So here we take the previous one, we need to take its bottom, that means we need to apply this mask, which is it? No, this is the first mistake, it's not 15. 1, 2, 3, 1, 2, 4, 8. It's actually, it has to be 8. Yeah, it has to be 8. There we go. That's the mistake. So you apply 8, and that extracts the bottom bit from here. So it extracts the bottom bit, and we moving it 2 bits to the right, making it the top bit, and that becomes part of the constraint. All right. So the only mistake I've made in here is like this. All right. I guess that's it. So what I would expect now, right? I would expect now the left column to be also generated according to the constraints that start from this left top corner, right? So that's what I would expect. So let's go ahead and run this entire thing. Let's go ahead and run it. So hopefully I'm not going to do any fucky wacky. There we go. So no segmentation faults, surprisingly. And are you guys ready? Look good to me. So the left top, the first left column seems to be correct. Does it look correct? I think it looks correct to me. So if you just scroll like this, I don't see any constraint mistakes in here. There's only constraint mistakes for the rest of these things, but we never actually generated any value for this thing. You know what I'm talking about? So we never actually generated anything here. Okay, so we already did half of the work. So the rest of the stuff we need to do, we need to just organize the nested loop that fills up the rest of the tiles according to their constraints. But this time we're going to have two constraints. So we have to take into account the top neighbor and the left neighbor. In case of the row, we only had to look at the left neighbor, and in case of the column, we only had to look at the previous neighbor. But here we have to look at the both neighbors, right? So we have to look at both of them. Right, and by the way, we can actually change the colors. So I mean, it doesn't necessarily have to be this sort of stuff. We can change it to something else. So I'm usually using complementary colors. So because they look good, so it could be something else. For instance, this. Does it look better? I don't know if it looks better. Also, we don't really seed our random number generator. We're using literally rand, which is bad for everything. Right? So as far as I know, there's usually two cases for random number generation, right? It's a cryptographic case, right? And also artistic case, right? An artistic case, in case of an artistic case, you want to have a full control over the random number generator, and you want to generate things in a particular distribution in a particular fashion. You know what's funny? The standard rand function is bad for both of the cases. It's kind of funny, like, and what other cases do you have a random number generator for? Like, so usually cryptographic one and artistic one. So in this case, we have an artistic one, right? We don't need a cryptographic one. I guess for a temporary things, just something. Blue, yellow. We can also take a look at other candidates. Multiply by width? Probably. Let me see. Did I multiply by height accidentally? Yeah, I did. Thank you so much. You're absolutely correct. It should be height. It should be width, because it's the size of the row. Yeah, thank you so much. It's just like they're equal, so everything works accidentally. Right, so thank you so much. So let's take a look at the other colors. So I think we also have something like this. I don't remember which one. I think it's a green and magenta, I think. Yeah, there's also this one. Pretty acidic, I would say. I think there's also black and white. Okay, so it's pretty fast. It's also there is black and white. So it actually looks pretty cool. So you can see that it's unfinished yet. So it is not very finished yet. So what I want to do actually, before we continue and finish the rest of the things, I want to make a small break and make a cup of tea and stuff like that. So yeah. All right, so let's finish this off. So the only thing that is left to implement in here is the rest of these things. Okay, so how are we gonna call it? I think the rest of the tiles. The rest of the tiles. The rest of the tiles. So we're gonna be iterating it row by row. So size t, and since the first left top left cell is already generated, we need to iterate starting from The wire is actually really annoying me in here, so it doesn't go away. So I probably need to unplug my tablet and just put it away. Right, so we're gonna be iterating from 1. Right. I'm gonna be iterating from 1. Less grid height in tiles, right? Because we're doing tiles. And similarly, we're gonna have size tx 1x less than grid width tl plus x. There we go. So that's what we've got. That's what we got. So we need to generate the position mask, and the value mask, right? And once we got this, we should be able to do something like grid width plus x, random tile v and p. There we go. So since let me actually draw that. So we have a pretty interesting situation. 1, 2, 3, 4. Right. So here is the top neighboring tile. So this is our top neighbor. Right, so then I'm gonna do it like that, and maybe I'm also gonna be doing something like this. 1, 2, 3, 4. It's almost worked. Okay. So I need to go in here. 1, 2, 3. Okay, so that's working. I forgot how to use Emacs. Alright, so these are the neighbors. Right, so this is that one, and this is the left one. Okay, so maybe we're gonna call this sort of like top neighbor, and this is the left neighbor, and this is the current G. Right, so that's what we're gonna have in here. In any case, so we only care about left and top, right? So if you have BLTR, right, we only care about left and top. So that means we need to combine it with 0, 1. Oh, this one is interesting. Left and top. So that means it's 0, 1, 1, 0. Right, and that thing will give us LTT. Well, it will give us, yeah. It will give us this thing. Yeah, left and top. So what is this value? 1, 2, 4. It has to be 6. Right, if I understand correctly, this is basically 6. Right, so because usually like this bit is equal to 1, 2, 4 and 8. Oh my god, 8. So, and you sum up only the ones and you get 6. So that means this thing is gonna be 6. Okay, so what about the value? What we want to do with t, we actually want to take its bottom and bring it to the top, and for this one we need to take its left and bring it to take its right and bring it to the left. So effectively we need to repeat these operations. Believe it or not, wait a second, this is literally these two things. This is literally these two things, except both of these things ORed together. This is very interesting. All right, so so this is the top row. So we can actually call this thing left P. Right, so this is the, oh my god, Emacs. Left P and left V. Right, so this is the left P and left V and left P. And this one could be top P, TV and TP. Right. So, and in our case, we want to actually have both, I think. So, yeah, we can just grab both of them and just combine them together, if you know what I'm talking about. Right, so in that case, that final, yeah, I can even do something like in a random, it's always TV. So LV or TV, LP or TP. Right. But in this case, this is going to be y multiplied by grid width TL. So this is going to be plus, but minus 1. And this one is going to be just plus x. Right. So yeah, and I don't even have to do anything. Right, so I just combine these things together. Right, so nothing particularly special is required in here, hopefully. So I think that is it, basically. And since it's like pretty much the same code, if it's pretty much the same code, maybe I can combine all of these 3 chunks into one. Maybe I won't be able to combine that one yet. I could try. I could! I think I even know how I can combine all of that. Oh shit. But this one is faster because there is no branching within the loop. If I combine all of that together, I'll have to add branching within the loop. So I basically made a more optimal version, but again, the compiler could optimize it itself without my help. I don't know. Essentially, so I could just have the 2-dimensional loop from 0 to width and 0 to height, right? And I could just check, do I have the left value? If I have the left value, this is going to be the mask that I'm going to be using. If I don't, just use 0. Do I have a top neighbor? If I do, just use this mask. If not, just use 0. Deep Singularity, hello, welcome to the stream. So, and that way I would be able to compress all of these chunks into like a single thing in here. I think. So yeah, let's give it a try and see if it's if we can compile it even. It compiles, but does it work? Let's find out. And it kind of worked. Grid rendering. It's actually rather interesting. So it's still faster than Atlas rendering, but we don't have that many tiles anyway. We don't have that many tiles anyway, so that's fine, I suppose. Anyway, so let's take a look at the final product. So, by the way, what's the color? So let's actually first set the color. Maybe we want to... Yeah, the color right now is black and white. So let's actually go back to yellow and blue and regenerate that one more time. One more time. Alright, so everything looks okay. So here's the atlas, right, so this is the atlas of these things, and here is the final grid. There we go. So this is what I spent 3 days on. Technically 4, but only 3 count. So that was the idea all along. This is basically Wang tiles. Yes, these are basically Wang tiles. Isn't it cool? Does it look cool? So it's procedurally generated and stuff. It is basically procedurally generated. So we can try to now change the shader that creates the tile set and maybe have different shapes. So this is the simple shape I could come up with. Also, we can change this stuff to black and white and just see how black and white is looking. Alright, so we're gonna use it like this. So that's pretty cool, actually, I think. Okay. So yeah, so we have that. It's kind of like, it looks like a bunch of blobs, but it's just because of the shader that we used. If we come up with a more interesting shader, for example, the one that uses metaballs, I think the pattern would be more interesting, right? But for now, it is what it is, because the main focus was on actually developing the engine that allows you to generate the atlas of the wank tiles from a single shader function, and then using that atlas it can generate the wank tile grid. So the main focus was on implementing this sort of engine, right? And we also parallelize the atlas stuff, and maybe we're also going to parallelize the grid stuff. So you know what I wanted to try? I wanted to try to reduce the size of the tile. Let's say that we're gonna have 32 by 32, right? So we're gonna have a very small tiles. So because of that, the rendering is gonna be super fast. Look at that rendering, right? So it's just nothing. Right, it's literally nothing, and the grid, everything is super small, right? So this is a very small grid. But now let's make the grid bigger. Right, how about making it, I don't know, 60 by 60. So we're gonna make a big grid. So grid generation, so this is the output. Grid rendering, so finally for the first time grid rendering was slower than the atlas rendering. Look at that. Right, so that's actually pretty interesting. So yeah, and now let's take a look at the so the atlas is very small, but the grid is this. So that's a that's a huge grid actually. Okay, we definitely need more interesting wank tile shader. Right, because right now you could have actually generated all of that without wank tiles, so that's the problem with this thing. You could just like, you don't need this kind of shit for wank tiles. Look like I made, believe it or not, Beatstream, this is literally what wank tiles are used for in game development. Yes, they're literally used for generating levels and mazes and stuff like that. I gave a link to like a website about wank tiles in here, so I'm gonna actually give it again because it's such an interesting website. And of course, just one more time in the description, cool wank tile site. So the wank tiles is basically the method of how you generate the grids, and what you need is just a tile set, right? So, and you can create whatever tile set you want. Each individual tile could be a piece of map that you're generating. So, for example, here you have a lot of different tile sets that can generate you this kind of stuff. So this is also generated using wank tiles, right? So for each tile in here, there's only like 2 matching colors, but in this case, these are not colors, right? These are things that can match together, right? And you can generate all sorts of different patterns and stuff like that. So this one is cool, actually. I think this one actually requires more colors, if you know what I'm talking about. So floor, H1, so this one is also cool. No, I know nothing about this game, I'm sorry. Is that a good game? Probably. We could try to generate the roads. And you know, the thing about our program, by the way, we're generating the wank tile grid, not from the tile set. We don't have a predefined tile set, that's the thing. We don't have a predefined tile set. We're generating it from a single shader, which accepts the bit mask that describes the tile, right? So it's 4 bits in a particular order. So each bit represents the side, bottom, left, top, right. 0 is first color and 1 is the second color. And UV coordinates within the texture of the tile. So you define a function that basically procedurally generates the texture of the wank tile, not the wank tile set, not anything, texture of the wank tile based on its description and UV coordinates, right? And then our engine generates the atlas, the whole tile sets, and then generates the grid. So to change how the tile set looks like, you need to change this small shader thingy that, given the bit, will change the appearance of this entire thing. Right, so that was the goal, and we can take a look at this thing. So where is the Wang function? Here's the Wang function. So this is how we defined it. So this is the single small thing. So we can try to define it somehow differently, I don't know. Let's find an optimal size of the tile. So let's actually make some 64 by 64. And this makes this 30 by 30, and in Wang, let's use maybe some other colors, I don't know, something like this. So it's going to be super colorful. Super colorful. And okay. So what's the slowest part? Yeah, so now since you have a big grid, Atlas rendering is actually nothing. So we definitely need to parallelize that part. Okay. And if I take a look at the grid, there we go. So this is the... Is it too bright, by the way? Is it too bright? I wonder if I can make it less bright somehow. Yeah, I'm rendering only on CPU. Fine for me. Okay. Ukrainian flag, by the way. Okay. So maybe we can copy paste this entire thing and make it a little bit more brightish, I suppose. So I want to replace ones with 75 and zeros with 25 maybe. Right, so maybe that will make it slightly less saturated, because I think it's a little bit too saturated. Right, and okay, so it's way less saturated now. So maybe 75 has to be 90 then, and this one has to be 10 then. There we go. Can you use CPU CMD to improve performance? Probably. Depends on where and depends on what kind of operations I'm using. So within the shader, probably I can. I'm not using anything that CMD is not using. It doesn't have, like we have min. Lerp is just, you know, multiplication and stuff like that. Yeah, I'm gonna add it to do, actually. So try to speed up the shader with CMD instructions. So I recently tried to speed up something that uses sine and cosine with CMD instructions, and I realized that it's a pretty bad idea. Right, so once you use sine or cosine, it's just like you're gonna have a lot of pain trying to... Because I think the only CMD instruction, I think it's from AVT 512, you have something weird for sine and cosine. The one thing I was thinking of is to build some sort of like a sine cosine table, but then I would need an operation that would interpret the numbers in the packed values as pointers, so I could query the sine and cosine table. So could approximate sine cosine maybe with look. LUT is a lookup table, right? Not sure how CMD works. It's just a buzzword for me. Well, I mean, I'm talking about lookup table, but here's the thing. So here's the sign, right? So you have x. So effectively, if you replace in a sign call with a lookup table, x becomes an address in memory. Before, x was just an angle, but now it's an address in memory. So now imagine that you have a bunch of values x, y, z, w, and you need to do a sign on them, on all of them simultaneously. So you need to simultaneously convert all of them into some sort of a pointer in your lookup table, right? And then you need some sort of a CMD operation that takes this you know, vector, this packed vector of pointers, and simultaneously queries them somewhere in the memory. And I don't think CMD has this kind of stuff. I don't think it has. I looked into that. Okay, so Intel intrinsic manual. So at least this is how I see that. I might be wrong actually. Maybe there's an easier way to do that, but if I'm going to be using lookup table, this is probably how I will have to do that. So it's load, right? So this is a load operation. Is there any other things? Do I have to like include all of them? This website is pretty janky, not gonna lie. Is it loaded? So there's a store operator. Ah, very well. Thank you so much. So I'll check it out later. I didn't find any Zig-Lang content by you. Is my search through too low? No, there's no Zig content by me because too many people keep constantly annoying me with this language, so I decided I'm not gonna do a Zig stream. I actually genuinely wanted to do a Zig stream, but since so many people are annoying me with this language, you know what? I'm not gonna do that. I'm not doing that stream anymore. So yeah. So there's only one condition. If somebody makes a donation, $300 donation with the message, do a Zig stream, only then I'll do a Zig stream. So yeah, Zig is $300. Anyway, so let's continue. So did I actually recompile the entire thing? It's actually, the saturation goes down dramatically. Right, what about like 5? And what's interesting is that I had this policy for quite some time already. People keep asking me about Zig, and I keep answering that it's $300 and nobody donated so far. So I make a conclusion, if you're a Zig programmer, you're not gonna make any money. So I don't think it's actually worth learning this language, guys. I think Zig programmers don't make any money on that language, so... Anyway, so let's continue. Go programmers, by the way, donated me a lot, right? Go programmers make like a bang every fucking day, but Zig programmers, too poor. The language don't bring any money. Okay, so this, I think this is fine. I think this is fine. Maybe I'm gonna actually do 99. Okay, so it's gonna be 99. Maybe I could probably automate this kind of thing. So maybe I could have like a single parameter and like it's done within a single parameter. Okay, so I'm happy with the saturation. What's interesting is that, so just changing by 1% changes so much of the saturation. It's insane. Maybe it has something to do with that, like, oh, it probably has something to do with the logarithmic precision and the gamma correction when the, you know, when the color is displayed on the screen. I think I know what it is. Okay. I think people are asking you about, because it looks like it would fit for your presence. Now, I looked into the language itself, like I briefly looked into the samples, and I think it's too noisy for my preference. So I don't think it's gonna be my the language of my choice. It's too syntactically noisy. All right, so, okay, so what I was doing, I think we need to commit this entire thing. In any case, Zig is $300. All right. You know what I would want? Right. I would actually like to have some sort of like a diagram that shows these you know, phases relative to the whole time. Right, as a like, so for instance, Atlas rendering took like 10% of the time, a grid generation took that percent of the time, and so on and so forth. So, and maybe we could also visualize it to see like which phase, how much part it takes, right, in the whole process. Of course, the slowest part is PNG generation, but I mean, who cares about PNG generation? Also, the labels are kind of scuffed in my opinion. You know what I want to do? I think I'm going to change the way we profile shit. I think we're going to change the way. I'm going to actually put the label after here. So that's going to be like this. Okay. Okay. Clock elapsed time 6 on Atlas rendering, so that's a little bit better. I think it's a little better. So also I'm gonna go to delete trailing white spaces and oh yeah, okay. So now, since we have something to show, right? We have something to show. Maybe we need to put that into the README. Right. So how are we gonna be putting that in the README? We can straight up put it there. Yeah, let's rename this thing into demo Atlas and demo grid. Right, and we need to update the README, right? Because in the original README, we just say, okay, think of it as a fragment shader. Here's the some tiles we generated. Here is, well, I mean, here is some tile sets we generated so far. So this is going to be demo Atlas PNG. Here's how a grid would look like with that tile set. Here, yeah. Here are some Wang. Okay, so let's put it this way, maybe. Here are some Wang tile grids we generated so far. So maybe we're gonna have several of them. So this is gonna be demo grid, and this one is gonna be demo grid PNG. Demo grid PNG. So, oh right. Okay, so this is gonna be Atlas, and this is gonna be the grid. Cool. And we don't really need the Atlas itself because we're not going to be demoing it. We're only going to show the demo grid, right? So maybe we also need to remove tile set. Okay, so let's go. More one tell it try speed of CMD instruction with parameter to limit. Live view generate, yeah, so we were working on this specific to do, so this one is done. Do we have anything else? Yep. So also had some to do's in here, maybe. Oh yeah, these are not really important. Yeah. If you think that C is my favorite language, you literally know nothing about me. I absolutely hate this language. Okay, so yeah, implement Wang tile grid generator, the actual Wang tile grid generator, and let's push that right at the rip. So I think I'm actually super happy with this engine that we got. Yeah, that's actually super cool. I really like that. So it would be interesting to generate more of such things. We're interested to generate more. The question is what we can do in there. Okay, so we have a wang. So these are like blobs and whatnot. So another thing we could do is basically literally just generate the colors on the sides, if you know what I'm talking about, right? Colors on the side. Let me see. So where is my paint? Okay, so this is gonna be that. So here is the tile texture, right? So, and what we can try to do, we can try to literally just generate like a stripe of a particular color in here. But the question is, if they intersect, right? If they intersect, how are we going to be combining these colors? We can actually combine them here, but that it adds additional dimension, additional color to the mix, so I don't think we can easily combine that. So maybe we could split this entire thing, so this color becomes like this, and this color becomes something like this, and it's going to be very similar to what we have in the website that I linked in here. So, but the only thing I want to have is just more different tiles. Yeah, you see here we just have like this triangle. Maybe that's what we want to do. Maybe we want to actually generate the triangle. Maybe we want to generate the triangle. So let's go. So maybe I need to also organize this kind of stuff differently. I'm already streaming for 3 hours. Do I want to continue? I'm not sure if I want to continue. So. So if you have a point, right? I suppose what you can do with that point, you can figure out the closest side for that point, right? You can try to figure out what's the closest in here, and then based on the closest side, right? Based on the closest side, you can figure out what kind of color you can put in there, right? And what's going to be the closest point? I suppose the closest point is going to be just one of those, right? I think I know. So essentially, well, you can just calculate the distance between all of them, right? So you can just literally take these distances and pick the smallest one, and here is your distance. And if you close enough to that specific distance, all right, you color it correspondingly, right? So that's going to be the idea, all right? And that probably will create that you know, iconic look of the tiles. So let's go. So this is going to be Wang blobs, right? So because it generates these blobs demo grid. So this is basically the blobs things. And let's try to recompile. So this is a Wang blobs. There we go. Wang blobs. And now we need to introduce Wang triangles, I suppose, right? I think it's a Wang triangles, right? Triangles. So now, so the distance, we need to actually get all of the distances in here, right? So, so the first distance is going to be the x value of this thing. So this is the first distance, right? UV x, right? So this is the first distance. The second distance, the second distance is effectively, ooh, 1 minus x, right? Yeah, I think so. You have the whole 1, you subtract this and you get 1 minus x. Okay, so 1 minus x, right? So this one is the left one, by the way, and this one is the right one. It's kind of important to keep them, to keep track of them, because we'll have to arrange them in a particular order, right? So because the order of the sides matter. Okay, so the next one is going to be the top one, which is just y, right? So UVC y. So this is the top one, and correspondingly 1 minus this thing is going to be the bottom one, right? There we go. So we have this kind of stuff. All right. So as we find the closest, right? As we find the closest. I feel like maybe we need to move the colors outside of the shader, because I think I'm going to be using the colors in all of the shaders. I think it does make sense. Right, so we have a global control over the colors. So, and yeah. So when we have this thing, RTLB, RTLB. So these are the distances, but the question is how and why and what. So by, I see. By figuring out the index of the distance that is the closer, we can now use that index. It's an index in the mask, and then we can extract bit from that mask, and we can use that bit for the color. That's the idea basically in here, right? Okay, so I'm a little bit tired because I've been streaming for 3 hours, so that's why I'm a little bit slow on such a simple task, so I really apologize for that. So let's actually put this into some sort of an array. All right, so this is going to be ds. We have 4 sides. ds stands for distances, right? So we're going to call distances. Okay. So, and we have a raid. Thank you so much for the raid. I cannot see who's that because I'm too far away. I'm sorry. Thank you for the raid. Really appreciate it. So less than 4, right? So this is going to be something like this, and essentially, so we're keeping track of the index, right? So we're trying to find the index. So maybe initially the index is going to be something like -1, right? And because of that, this is going to be something like int. And if index is less than 0, or the ds index is greater than dsi, right? We need to update the current index, right? We need to update the current index. So yeah, so this is the negative, then we find the smallest index in here. So this is the smallest index. And that index will help us to find this stuff. So that index is basically how many times we have to, you know, shift the BLTR. Yeah. Right, if it's going to be 0, that means BLTR already contains a 0, and there we go. So then we just use the caller. Okay, so then we do caller, BLTR 1, and then we just return that caller. Okay, so that's the whole process actually of generating that triangle. Right, so you're figuring out the closest distance, right? So here's the closest distance. Then you use that index to shift the bits correspondingly, and then you use that bit for the colors. So that should be it, I think, hopefully. So here's the blob, wang, blob. Okay, so this one is the triangles. There we go. And let's just try to compile the entire thing. Okay, so this has to be colors. There we go. Has to be colors. Alright, so let's make a very scary thing. Let's try to generate the whole shit. Is it gonna suck fault? It didn't suck fault. Okay. So Atlas rendering was really fast. Grid generation was not affected. Okay, so let's take a look at the Atlas. So this looks legit actually. This looks like a proper. It actually looks like this. Yeah, we literally generated this. Okay, so we literally generated this, and if we take a look at the grid that was generated from this thing, there we go. So this is actually pretty good, generation. So, Wang tiles, everyone. Wang tiles. It's pretty pogue. Yeah. So. Yeah, we basically did this thing. You know what I was thinking about? I actually wanted to have like a, something in the middle, right? Some other color in the middle. Maybe black, maybe white or whatever. So we could try to do that by actually limiting what's the minimum distance, right? So if the distance is, if the minimal distance is too big, it's going to be a completely different color. So we're going to have stripes around the edge, right? So we're going to have stripes around the edge. Rand triangle. Where is the triangles? Triangles. There we go. So and the way we can do that, if the S index is greater, so if it's close to half, it has to be something like 25. Right, if it's greater than 25, we're instantly returning, you can even do it like that. Just instantly return black, I suppose, like 4FS, actually 3F because it's RGB. And it's just black. Otherwise, just return whatever is supposed to be here. Okay, that looks fine. So that might be a little bit more interesting now. Who knows? We'll see. We can even, you know what? I have other interesting ideas. So let's take a look at the Atlas. Okay, so that's exactly what I wanted. So I wanted them to be an actual grid and whatnot. So look at that. That's pretty cool. So this is the tile set, and let's take a look at the grid itself. It looks like numbers or something. That's cool. That's fucking cool. Look at that. This shit is cool. I love it. Oh fuck, this is so cool. I love shit like that. Oh my god. You know, I would also like to have, because for each tile you have an associated number, right? So for each tile you have an associated number. So you can associate the number of the tile with the color at the center, right? With some sort of a color at the center. So each cell inside is going to have its own color, but on the edges they're going to be actually... Oh shit, I have an idea. I even know what kind of stuff we're going to have in there. It could be a gradient for a particular thing, for a red, for instance, right? So if it's that, we can effectively just take the original BLTR, right? So this is the original BLTR, and we are converting it to float, and we're dividing it by 15. There we go. So we have the intensity of some sort, right? So it's going to be float T. Right, so this is going to be the intensity, and then we can put that intensity somewhere here as the, for instance, red color. But for the rest of the things, we can put something like 10. 10. There we go. So, and this is not S, it's actually F. Right, so that can produce more interesting tiles because they're going to have something interesting at the center, like basically gradation based on their BLTR. right? So yeah, so you see, the bigger it is, the gamma correction. I think we need to perform a gamma correction on this thing. Just a second. So I probably need to just grab this thing, because you see, this thing grows. The intensity doesn't grow linearly, particularly. It's actually like basically black at the beginning, and it jumps to red like to the end. So it's really, really sus. This is because we don't perform a gamma correction. So let's actually try to do a gamma correction. So this is the coefficient to which we have to raise the entire shit. So it's vector 3f to the power. I'm gonna put it like that, and hopefully that will produce a better result. I don't know, we'll see. We'll see, we'll see. Okay, so here's the atlas. Yeah, now it's a little bit better. Do we agree that it's a... Well, I mean, this one is actually kind of sus. Well, it's not sus, actually. That's precisely how it has to be. Yeah, so it's more linear now. It's more linear. Yep, that's what I wanted. So, if you want to know more about gamma correction, watch the Minute Physics video about how computers get the color wrong. I think it's related to the gamma correction. Yeah, it is related to gamma correction. Minute Physics gamma correction. Yeah, this one. So if you want to know more about what I just did, watch this video. It's actually a very short video, and it explains the entire situation really well. Right, and specific number I think I actually took from the Learn OpenGL article. So let me actually put that in the description. So it's gonna be Minute Physics on computer, on color in computers. Right, so gamma correction. Yeah, so the specific coefficient I took from this article. Right, it talks about the same thing. Yeah, perceived linear brightness, like the physical linear brightness, and so on and so forth. It literally talks about it. So, and that specific coefficient is from here, right? So you can just roughly raise it to the power of 1 over 2.2, and it will just sort of correct it, like approximately. Sort of. So this one. Okay, so here's the thing. And now let's take a look at how the grid looks like with this stuff. Yeah, it looks like shit. I was hoping for something more interesting. Yeah. You know what I'm thinking about, shit? You know what I'm thinking about? So we're sort of transitioning from yellow to blue, right? Maybe the actual color in here is going to be transitioning from yellow to blue, basically. Why not? So let's quickly do that. So how I'm going to be mixing all that? I suppose it's going to be lerp, vec3f, lerp, right? And we're going to have a first color, so it's going to be colors 0, colors 1. Right, and we're transitioning with this thing, vec3fst, and of course, after that, we have to also gamma correct it. So this one will be vec3f. So let's call it something like result. And we're gonna just do something like result. There we go. The grid eats up all of the bit rates. It is what it is, and it isn't what it isn't, is it not? Okay, so that is very fucking interesting, mate. Look at that. Shit, bruh. That looks cool. Do you see that? Okay, so this is the tile set, right? It's just a tile, it's an atlas. Now let's try to generate a grid with that. We can maybe, okay, so I can increase the size of the tile, 128, and decrease the size of the grid, 15. So it's going to be a little bit closer now. Right. Okay, so the atlas is a little bit bigger now, so this is the actual atlas, and the grid is like this. So, holy fuck, this looks dope as fuck. And this is procedurally generated on CPU, by the way. Looks dope. I really like that. And if you want to know how quickly it generates the entire thing, right? So the resolution of this thing is, well, it's 2K by 2K. It's 2K by 2K, right? And the actual time it takes to generate this kind of shit is less than a second, right? So it takes less than a second to generate all of that. So here is like times. So the longest time here is a PNG generation. Atlas rendering is actually multi-threaded in here. So I also want a multi-thread grid generation. I mean, grid rendering. Look, grid generation doesn't need to be multi-threaded. It's like less than millisecond. Like you can't even perceive that. But grid rendering is bigger than even Atlas rendering. So that thing definitely needs some sort of, you know, multi-threading. You can add some noise. That's not a bad idea, actually. It's not a bad idea. So, but not really some noise, but maybe. So the main problem with this style set is that on 0 it blends with the center, and at 1, well, it almost blends with the center as well. So it only doesn't blend somewhere in between. So I have an idea. What if we shift those mother flippers a little bit, maybe? I guess it's fine. We can try. Rank triangles. So maybe BLTR is going to be, oh boy, plus 8. Right, mod 16. Something like that. And of course I need to review the whole thing. So is it gonna look good? If it's not gonna look good, I'm gonna actually go and... Yeah, it still blends with some of them. Still blends with some of them, and the actual grid is... It's more interesting, to be fair. It is more interesting. Oh, I have an idea. What if we reverse the entire thing? Yeah, okay, so I have a better idea. So over 16 and then -1. Okay, so that should be better. So now I don't think anything should blend. Perfect. That is fucking cool. So that's a cool set. Grid. Now we're fucking talking. We can also try different colors. Right. So, so what colors do we want? Black and white? How about black and white? Okay. Pretty pale. Pretty pale. I think it's pretty pale. So which one do you like? I think this one is cool. Maze, yeah. It's amazing. Oh. So in the demo grid, so the size of this, I think the size of the thing is too huge. We need something smaller for the demo. Let's try to reduce everything by half. So what about 64? I don't like the, with squares in the middle, but I like it overall. Okay. Okay, so let's get the file. Can you make it even smaller? What about 32? Maybe that's fine. So this is grid. Basically 1000. I think this number is actually fine. Okay, so this is going to be demo 001, right? So this is a demo 001, and for the demo 002, we're gonna have blobs, not triangles. Let's actually rename it to digits. Digits, boom, boom. Blobs. Okay. Ah, shit. So. Yeah, so this is the blobs. Maybe blobs should be, I don't know, they're too desaturated probably. And also, here's the thing, I forgot that we need to seed our random number generator. So I'm going to do srand times 0. Right, so it should produce different results every time. Thread pool, I just create a bunch of threads, pthread create. Like this. So I split the job into sub-jobs, I create the threads, I wait on them, and then I just quit. So that's how it's done. So luckily, the job is actually easy to parallelize this way. Okay, so let me take a look. So now it's slightly different. Okay, so this one is going to be demo 00. So we have demo 00, demo 01. Maybe it should be brighter. It feels like I want it to be brighter. Okay. What about that one? Okay, so I like this one. Shit. Okay. 0, 0. So that one. And all of that is generated with the same engine. We're just substituting the shader. Right, so we have a simple function that acts like a shader, and yeah, so just like uses that function, and with this function you can produce the results like this, which is kind of cool, I'm gonna lie. Yep. So let me see. Here are some Wang tile grids we generated so far. So this is going to be demo 00, 00, 00, 01. Okay, so so let's do a committee for these things. I'm gonna remove that. Yeah. Implement digits shader and add more demos to readme. So I'm gonna push that right into the repo. Kids can be asked to recognize the 8, 9, 3, etc. Probably. Yeah, I can see 3. Oh, this is actually pretty cool. Yeah. Not bad though. Yeah. Okay, so maybe at some point we're gonna add more tiles or something. So I edit all these things in the readme. So yeah, it's pretty dope, isn't it? I think it is. Again, all of that is generated with the same engine, based on the idea of Wang tiles that you can read more about in here. I do not recommend reading Wikipedia article on Wang tiles, by the way. You're gonna be sad if you try to read it. So you're gonna be very, very sad if you try to read this article. It's a very sad article. Just read this one. Yeah, so this one is way better. There's also a couple of examples that you can play with. If you're interested in this kind of stuff. Yeah. Okay. So you can find the source code of the entire thing here in the chat or in the description if you're watching it on YouTube. And it's completely open source and under MIT license. You can do whatever you want with it. You can play with it, study it. I also published the recordings of me developing this entire thing on this YouTube channel. So if you want to go back, there's a playlist for wank tiles in there. So you can watch me developing this thing from scratch. So it's pretty much at the state where I'm happy with this entire thing, but there's still a couple of to-dos that would be interesting to address, right? So yeah, I would like to implement the tiles based on metaballs. That would be kind of cool. Right, so based on the metaballs. So another thing, yeah, metaballs is like these things, so they sort of stick to each other. So another thing would be using CMD instructions in the shaders. They're not really shaders, but I'm just, you know, referring to them as shaders because they basically map UV coordinates to RGB coordinates. So they act like fragment shaders. So it'll be interesting to speed up, like we're using CMD instructions. It will be also interesting to, you know, implement like a runtime parameter that limits the amount of threads, so you don't use more threads than needed. So live view with SDL, like instead of like saving it to a file, it would be kind of cool to view in real time the tile grid and maybe modify some parameters and stuff like that. So and I think we also need to parallelize the grid rendering. So another thing I would like to do parallelize grid rendering. That'll be kind of cool. So there's a lot of things to do in here, and I'm not sure if I'm gonna do them because I kind of got the gist of the wank tiles, and next time I'll actually need to implement them. I'll probably know how to do that. So yeah. Okay, to parallelize grid rendering, and I'm gonna push that right into the repo. All right, so do you have any plans on 3D wank tiles? I didn't think that you can actually expand it to 3 dimensions. I suppose you can. So you have 6 sides, right? So you need 2 to the power of 6 things. This is not how we do that in Python. 64 tiles. Okay, generating 64 tiles is not. How are you gonna render that though? So they're gonna be cubes. How are you supposed to see inside of cubes? I suppose you can use. Okay, let me see. You can probably use wank, like 3D wank tiles for generating like a cave system, right? So if you have like single cubic wank tile, right? So something like this. You can imagine that side with 0 is solid side, and side with 1 is the one with the hole, right? And you have a bunch of holes in here, and they connect to each other, right? Something like that. So this could be sort of this 3D wank tile system, and you generate a maze, like a cave system with this kind of thing. I could imagine that. So for caves with holes, okay. So all right, sounds interesting. Maybe at some point we can do that. I don't know. I'll keep that at the back of my head. Minecraft. Does Minecraft use wank tiles for this kind of stuff? I don't think so. I'm not really sure if it does. I don't know, maybe. Alright, so I've been streaming for almost 4 hours, so I guess it is time for me to go, boys and girls. Thanks everyone who's watching me right now, I really appreciate it. Check out the description if you're watching on YouTube. Check out the YouTube if you're watching on Twitch. By the way, we're uploading all of that on YouTube if you missed something, so it's gonna be there. And yeah, I see you all next time. Love you. Bye.